Numbers are the most fundamental language of the universe. It is the concept that allows everything else in mathematics to exist. Before shapes, before equations, before the vast and intricate structures of higher mathematics, there is number. A single, quiet idea that underpins all of it. At its most basic, a number is a way of expressing quantity. How many? How much? How far? A shepherd counting sheep on a hillside at dusk, a merchant measuring grain by weight, a child placing stones in a row to understand that 3 is more than 2, all of them are engaging with the same ancient idea. Number is older than writing. It predates every formal system of knowledge humanity has ever constructed. Long before words were carved into stone, marks were being made to represent quantities. Tally marks on bones dating back tens of thousands of years show that the human mind has always reached for number as a way of making sense of the world. Numbers begin simply 1, 2, 3, a progression so natural it feels instinctive, because in many ways it is. Children grasp the idea of more and less before they can speak full sentences. The recognition that a group of 4 objects is different from a group of 5 is not taught so much as awakened. It is a perception that seems woven into the fabric of conscious experience itself. But numbers do not stay simple for long. From counting numbers, mathematics gradually expands outward in every direction. The discovery that quantities could be split led to fractions. The need to describe what lies between whole values gave rise to decimals. The recognition that subtraction could reach beyond 0 introduced negative numbers. Each expansion of the number concept was not an invention so much as an uncovering, a gradual revelation of structure that was already quietly present, waiting to be noticed. Numbers also carry a strange and beautiful duality. They are simultaneously abstract and concrete. The number 7 has no physical form. It cannot be touched, weighed, or placed on a shelf. And yet 7 apples, 7 days, 7 notes in a musical scale. The abstraction takes on weight and texture the moment it is applied to the world. This movement between the abstract and the real is one of mathematics' most enduring qualities, and it begins here, at the very concept of number itself. Across every human civilization, independently and separated by oceans and centuries, number systems emerged. The Babylonians, the Egyptians, the Maya, the ancient Chinese, each culture arrived at the same underlying truth through entirely different paths. This convergence is not coincidental. It reflects something deep and universal. Number is not a human invention placed onto a neutral world. It appears to be a feature of the world itself, one that the human mind is uniquely shaped to perceive, to name, and to explore. Number is where mathematics begins, and in many ways, counting. Counting is the first act of mathematics. It is the bridge between the abstract idea of number and the tangible reality of the world. To count is to establish order, to assign sequence, to say with certainty that this comes before that, and that together they amount to something measurable and known. It is one of the oldest and most deeply human of all intellectual activities. The act of counting begins with a simple correspondence: one object, one number, another object, another number. This pairing, so intuitive it seems almost automatic, is actually a profound logical operation. It establishes a relationship between the physical world and the abstract world of number. A child touching each apple in a bowl and quietly saying 1, 2, 3, 4 is performing an act of mapping, connecting a sequence of sounds and symbols to a sequence of real, separate things. The last number spoken is not just a label, it is a summary. It tells the whole story of the group in a single word. This principle, known in mathematics as one-to-one correspondence, is the foundation upon which all of counting rests. 2 collections of objects are equal in number, not because they look the same, but because they can be paired perfectly, one-to-one, with nothing left over on either side. Ancient peoples used this principle long before formal number systems existed. A herder might match each sheep in a flock to a stone in a pouch, not by knowing the number 30, but by knowing that when the sheep returned at evening, each stone should have a partner. The correspondence itself carried the information. Counting also introduced humanity to the idea of sequence. Numbers do not merely exist, they follow one another in a fixed and reliable order. 1 always precedes 2, 2 always precedes 3. This ordering gave the world a sense of structure that extended far beyond mathematics. The sequence of days, the progression of seasons, the stages of a life, all of them borrowed their logic from the simple, steady march of counting numbers moving forward without interruption. As civilizations grew more complex, so did the demands placed on counting, tracking harvests, recording debts, measuring land. all required counting systems that could handle larger and larger quantities without becoming unwieldy. Different cultures responded by developing grouping strategies, counting in tens, in 20s, in 60s. These groupings became the foundations of number systems, each one a way of managing the endless forward progression of count by organizing it into structured, repeating units. What makes counting remarkable is not its complexity, but its universality. Every mathematical structure, however abstract or advanced, traces a line back to this singular, quiet act. Calculus depends on number. Number depends on quantity. Quantity depends on counting. Strip away everything formal and technical, and at the very base of the entire discipline, there is simply someone, somewhere, beginning at 1 and moving steadily forward. 0. 0 is the most unusual number in all of mathematics. It is the number that represents nothing, and yet its presence changes everything. Before 0 existed as a formal concept, mathematics was a limited and often cumbersome enterprise. After 0, it became something capable of describing the deepest structures of reality. Few ideas in the entire history of human thought have carried more consequence packed inside a single symbol. The earliest number systems did not include 0. For a long time, there was simply no need to write down the absence of something. If a merchant had no grain, he wrote nothing. The blank space carried the meaning, but as mathematics grew more sophisticated and as the need to perform complex calculations became more pressing, the limitations of this approach began to show. A placeholder was needed, a symbol that could occupy a position in a number and indicate that nothing of that value was present. The number 305 and the number 35 are entirely different quantities, and the only thing separating them is a 0 holding the tens position open. Without it, the distinction collapses. This placeholder function was the first role 0 played, and it was revolutionary on its own. But 0's deeper significance emerged when mathematicians began treating it not merely as a placeholder, but as a number in its own right, a quantity that could be added, subtracted, and reasoned about like any other. The ancient Babylonians gestured toward it. The Maya developed their own version independently, but it was mathematicians in ancient India who first treated 0 as a true number and began exploring what it actually meant to calculate with nothing. What they discovered was strange and fertile. Adding 0 to any number leaves it unchanged. Subtracting 0 does the same. 0 sits at the center of the number line, the precise boundary between the positive and the negative, a point of perfect stillness between two infinite directions. Multiplying any number by 0 collapses it instantly to nothing, regardless of how large that number was. A billion multiplied by 0 is 0, with the same quiet finality as 1 multiplied by 0. Dividing by 0 is another matter entirely. It produces not a very large number, or a very small one, but something mathematics cannot resolve. An undefined result that sits outside the boundaries of ordinary arithmetic. This peculiarity has fascinated mathematicians for centuries and continues to appear at the edges of advanced mathematics and physics, wherever calculations approach conditions of extreme density or singularity. Beyond arithmetic, 0 became the anchor of coordinate systems, the starting point of measurement, the origin from which all other positions are defined. In calculus, the behavior of functions approaching 0 unlocks the entire theory of limits and derivatives. In logic and computing, 0 and 1 together form the binary language that underlies every digital system on Earth. Addition. Addition is the first operation of mathematics. It is the process of bringing things together, of combining separate quantities into a single unified whole. Where counting moves forward one step at a time, addition takes a larger stride, collapsing a sequence of individual counts into one fluid motion. It is simple enough for a child to grasp in their earliest years, and deep enough to underpin some of the most advanced structures in all of mathematics. The intuition behind addition is ancient and physical. 2 stones placed beside 3 stones make 5 stones. 4 days of travel followed by 3 more makes 7 days total. This combining of quantities is so natural, so immediately legible to the human mind, that it feels less like a learned operation and more like a recognition, a noticing of something the world already does on its own. Groups merge. Quantities accumulate. Addition is simply the language mathematics developed to describe that process precisely. At its most fundamental level, addition is defined by 2 properties that hold without exception. The first is commutativity. The order in which 2 quantities are added makes no difference to the result. 3 added to 5 produces exactly the same total as 5 added to 3. The numbers may be arranged differently, approached from different directions, but the sum remains unchanged. The second property is associativity. When three or more quantities are added together, the way they are grouped during the process does not affect the final results. Adding 2 and 3 first, then adding 4, produces the same answer as adding 3 and 4 first, then adding 2. These properties seem almost too obvious to be worth stating, and yet they are the structural guarantees that make arithmetic reliable, consistent, and infinitely scalable. As numbers themselves expanded into fractions, into decimals, into negatives, addition expanded alongside them. Adding a negative number introduced the idea that combining quantities could also mean reducing them. Adding fractions required finding common ground between different ways of dividing a whole. Adding decimals demanded careful alignment, a precise accounting of place value to ensure that tenths were meeting tenths and hundredths were meeting hundredths. In each case, the underlying operation remained the same, but its application grew richer and more nuanced. In higher mathematics, addition takes on forms that would be unrecognizable to a child stacking stones, yet remain governed by the same essential logic. Vectors are added by combining their components. Matrices are added entry by entry. Functions can be added together to produce new functions. Even in the abstract structures of modern algebra, where the objects being combined bear no resemblance to ordinary numbers, the operation that joins them is almost always some form of addition, preserved and generalized across centuries of mathematical development. Subtraction. Subtraction is the mathematics of removal. It is the operation that describes what remains when something is taken away, when a quantity is reduced, when the world contracts rather than expands. Where addition is the language of accumulation, subtraction is the language of loss, of distance, of the gap between what was and what is. Together they form the two most fundamental directions in all of arithmetic, and neither one is fully understood without the other. The physical intuition behind subtraction is as immediate as the intuition behind addition. A bowl that held 7 pieces of fruit and now holds 4 is telling a story of subtraction. A journey of 10 days with 3 already completed has 7 remaining, a debt, a diminishment, a departure. All of these are experiences the human mind reaches for subtraction to describe. Long before any formal system of mathematics existed, people were reasoning about what remained after something was removed. Subtraction is not a construction imposed upon the world. It is a reflection of something the world does constantly, quietly, and without ceremony. In its most direct form, subtraction is the inverse of addition. To subtract is to ask which number, when added to the one being subtracted, would return us to where we started. 8 minus 3 is 5 because 5 and 3 together make 8. This inverse relationship is one of the most important structural features of arithmetic. It means addition and subtraction are not two separate operations so much as two directions of the same one, moving forward and backward along the same number line with equal ease. For a long time, subtraction seemed to have a natural boundary. You could take 3 from 8, but could you take 8 from 3? Within the counting numbers, the answer appeared to be no. The question produced no meaningful result inside a system where numbers began at 1 and moved only forward. But the need to describe temperatures below a reference point, debts that exceeded assets, positions behind a starting line, all of these pressures gradually pushed mathematics to expand its understanding of what subtraction could produce. Negative numbers were the answer. The number line extended backward past 0, and subtraction was freed from its boundary, able to move in either direction without constraint. This expansion transformed subtraction from a simple reduction into something more geometrically rich. The result of a subtraction now carried not just magnitude but direction, indicating not only how far apart two quantities were, but which side of 0 the answer fell on. The difference between two numbers became a measure of signed distance, a concept that would eventually reach into algebra, calculus, and the mathematical description of physical space. In everyday life, subtraction governs budgets and balances, schedules and shortfalls, measurements and margins. In advanced mathematics, it underpins the concept of difference that drives derivatives, the notion of error that drives statistics, and the idea of distance that drives geometry. Multiplication. It is the mathematics of scaling. It is the operation that describes not just combining quantities, but expanding them by a factor, growing one number by the measure of another. Where addition accumulates gradually, one unit at a time, multiplication leaps. It compresses what would otherwise be a long and tedious sequence of additions into a single elegant operation. It is the point where arithmetic begins to feel not merely useful, but genuinely powerful. The simplest way to understand multiplication is as repeated addition. 3 multiplied by 4 is the same as 3 added to itself 4 times. 5 multiplied by 6 is 5 groups of 6, laid end to end and counted as 1. This interpretation makes multiplication feel like a natural extension of what came before, a faster path to the same destination. And for small whole numbers, this is a perfectly satisfying way to think about it. Children learning multiplication tables are essentially memorizing the results of repeated additions, compressing them into instant recall so that the mind does not have to laboriously retrace each step every time. But multiplication quickly reveals itself to be something richer than accelerated addition. It has its own properties, its own symmetries, its own behavior that deserves to be understood on its own terms. Like addition, multiplication is commutative. 3 multiplied by 4 produces the same result as 4 multiplied by 3. This may seem obvious when stated, but it carries a quiet geometric elegance. A rectangle 3 units wide and 4 units tall contains exactly the same number of unit squares as a rectangle 4 units wide and 3 units tall. Commutativity here is not just an algebraic rule, but a visual truth, a symmetry you can see and measure. Multiplication is also distributive over addition, a property that becomes one of the most frequently used tools in all of algebra. Multiplying a number by a sum is the same as multiplying it by each part of that sum separately and then adding the results. This single property underlies the expansion of brackets, the factoring of expressions, and countless techniques that carry mathematics from simple arithmetic into the broad landscape of symbolic reasoning. As the number system expanded, so did the behavior of multiplication. Multiplying by a fraction scales a quantity downward rather than upward. Multiplying by a negative number reverses direction. Multiplying by 0, regardless of the scale or complexity of what came before, returns everything to nothing. Multiplying by 1 leaves everything unchanged. These special cases are not exceptions or complications. They are windows into the deep structure of how numbers relate to one another, how identity and annihilation and direction are all encoded within a single operation. In physics, multiplication describes force and acceleration. In finance, it drives compound growth. In geometry, it scales shapes and transforms spaces. In advanced mathematics, it generalizes into operations between vectors, matrices, and abstract algebraic structures of extraordinary complexity. Division is the mathematics of sharing. It is the operation that takes a quantity and asks how it can be separated into equal parts, distributed evenly, broken down into its constituent measures. Where multiplication scales upward, division scales downward. Where multiplication expands, division resolves. Together they form the second pair of inverse operations in arithmetic, two directions of the same fundamental relationship, each one undoing what the other builds. The physical intuition behind division is immediate and ancient. 12 pieces of bread shared among 4 people, a length of rope cut into equal segments, a harvest distributed across a community according to some principle of fairness. These are not abstract mathematical problems. They are the ordinary negotiations of daily life, the practical questions that every human society has always had to answer. Division is the operation that mathematics developed to handle them precisely, to move beyond the approximate and the estimated toward the exact and the reproducible. At its most direct, division is the inverse of multiplication. To divide 12 by 4 is to ask which number, when multiplied by 4, returns 12. The answer is 3, because 3 groups of 4 reconstruct the original quantity exactly. This inverse relationship means that division and multiplication are not separate operations but complementary perspectives on the same underlying structure. Every division statement is simultaneously a multiplication statement. Read from the other direction. But division introduces something that the previous operations did not. It introduces the possibility of a remainder. When a quantity does not divide evenly, something is left over, a residue that cannot be cleanly distributed within the chosen unit. 23 divided by 4 produces 5, with 3 remaining. This remainder is not a failure of the operation, but a piece of genuine mathematical information. It tells us something about the relationship between the two numbers involved, about the degree to which one fits inside the other. Remainders became the foundation of modular arithmetic, a branch of mathematics with deep implications in number theory, cryptography, and the structure of modern computing. Division also forced mathematics to confront fractions. When 7 is divided by 2, the result is not a whole number. It falls between 3 and 4 at the point we call 3.5. Rather than treating such results as incomplete or problematic, mathematics embraced them, extending the number system to accommodate every possible ratio between whole numbers. The result was the rational numbers, an infinitely dense collection of values filling every gap between the integers, all of them born from the simple act of dividing one whole number by another. The one boundary division cannot cross is 0. Dividing by 0 produces no meaningful result, not a very large number or a very small one, but something genuinely outside the reach of ordinary arithmetic. This boundary has fascinated and challenged mathematicians for centuries, appearing wherever physical systems approach extremes of density or singularity. Fractions. Fractions are the numbers that live in the spaces whole numbers cannot reach. The values that emerge the moment a unit is divided, and the pieces are considered not as remainders to be discarded, but as quantities worthy of their own names. A fraction does not describe a failure to reach a whole number. It describes something precise and real, a portion of a whole that has been measured, named, and made available for calculation. The idea of a fraction is as old as the idea of measurement itself. The moment a human being first tried to divide something physical, a length of rope, a portion of land, a measure of grain, and found that it did not divide into a whole number of equal parts, a fraction was born. Ancient Egyptian mathematicians developed sophisticated systems for working with fractions thousands of years ago, representing them in ways that allowed precise calculation of areas and volumes. The need for fractions did not arise from abstract curiosity. It arose from the practical demands of a world that does not always divide evenly. A fraction is written as one number placed above another, separated by a line. The number below, the denominator, tells how many equal parts the whole has been divided into. The number above, the numerator, tells how many of those parts are being considered. 3/4 means a whole divided into 4 equal parts, with 3 of them present. 1/2 means a whole divided into 2 equal parts, with 1 of them taken. The denominator names the unit, the numerator counts it. Together they locate a quantity with perfect precision anywhere between 0 and the integers above. Fractions inhabit the number line in extraordinary density. Between 0 and 1 alone, there are infinitely many fractions. Between any two fractions, no matter how close together they appear, there are infinitely many more. This property, known as density, means that the rational numbers, all the fractions that can be formed from whole numbers, pack themselves into every interval of the number line with inexhaustible thoroughness. And yet, as mathematics would later discover, even this infinite density leaves room for other numbers entirely, the irrationals that slip through every gap the fractions leave behind. Operating with fractions requires attention to the relationship between denominators. Adding or subtracting fractions demands a common denominator, a shared unit that allows the numerators to be meaningfully compared. Multiplying fractions is more forgiving, requiring only that numerators multiply together and denominators multiply together. Dividing by a fraction inverts it and multiplies, a rule whose elegance rewards careful reflection. Each of these operations extends the arithmetic learned with whole numbers into a richer and more flexible domain. In science, fractions describe concentrations and proportions. In music, they define the relationships between note durations. In probability, they measure the likelihood of events. In the deepest reaches of number theory, the behavior of fractions reveals profound truths about the structure of the integers themselves. Decimals. They are the mathematics of precision. They are a way of expressing quantities that fall between whole numbers, written not as one number placed above another, but as a single continuous figure extending to the right of a point. Where fractions describe portions through the language of division, decimals describe them through the language of place value, extending the same system that organizes whole numbers rightward past a boundary marker into an expanding sequence of smaller and smaller units. They are fractions in a different dress, offering the same information with a different clarity and a different ease of use. The decimal system is built on powers of 10. To the left of the decimal point, each position represents a value 10 times larger than the one to its right. To the right, the relationship reverses. The first position after the decimal point represents tenths, 1/10 of a whole unit. The second position represents hundredths, 1/10 of a tenth. The third represents thousandths. Each step rightward divides the unit by 10 again, producing a finer and finer resolution, a more and more precise account of where a quantity actually sits. A measurement of 3.7 is 3 whole units and 7/10 of another. A measurement of 3.74 is the same 3 and 7/10, plus 400ths more, pressing closer still toward exactness. This extension of place value was not an abrupt invention, but a gradual recognition. The positional number system that gave whole numbers their elegant efficiency was always capable of extending in both directions. Once mathematicians and scientists began working with measurements that required finer distinctions than whole numbers allowed, the decimal point emerged as a natural and necessary notation, a simple marker indicating where the whole units ended and the fractional parts began. Decimals brought a practical ease to calculation that fractions sometimes resist. Adding and subtracting decimals follows the same alignment rules as adding and subtracting whole numbers, provided the decimal points are kept in column. Multiplying decimals requires only the counting of decimal places to position the point correctly in the result. This computational simplicity made decimals the preferred language of science, engineering, and commerce, where calculations must be performed quickly and accurately across many steps without the complexity of finding common denominators or reducing fractions to their simplest form. Some fractions translate into decimals that terminate cleanly. 1/4 becomes 0.25, arriving at its destination in 2 decimal places and stopping. Others produce decimals that repeat, cycling through the same sequence of digits indefinitely. 1/3 becomes 0.333, the 3 extending without end. 1/7 produces a repeating cycle of 6 digits that returns to its beginning and loops again forever. These repeating decimals are not approximations. They are exact values, precisely equal to the fractions they represent, their repetition a consequence of the relationship between the fraction's denominator and the base 10 system. Negative numbers. Negative numbers are the mathematics of below. They are the numbers that exist on the other side of zero, extending the number line in the direction opposite to counting, giving mathematics a way to describe not just quantity but position, not just magnitude but direction. Before negative numbers, arithmetic could only move forward. After them, it could move in 2 directions simultaneously, and the entire landscape of mathematics opened outward in ways that would take centuries to fully explore. The resistance to negative numbers was long and surprisingly stubborn. For much of mathematical history, a result that fell below zero was treated not as a meaningful answer, but as evidence that the problem had been incorrectly posed. If subtracting a larger number from a smaller one produced something below nothing, many mathematicians simply declared the operation impossible and moved on. The idea that a number could be less than nothing seemed to contradict the physical intuition that number was fundamentally about counting things that existed. You could have 3 apples or 7 apples, but you could not have -2 apples sitting in a bowl. What changed was not the mathematics, but the interpretation. Negative numbers became accepted, not as quantities of objects, but as positions and relationships. A temperature of -10 is not an absence of 10 degrees, but a location 10 degrees below a chosen reference point. A financial balance of -50 is not 50 units of nothing, but a debt, a displacement from zero in the direction of owing, rather than having a submarine 50 meters below sea level, is not at an impossible position, but at a real and precisely defined one, described naturally and exactly by a negative number. The abstraction became useful, and usefulness is what ultimately earns a mathematical concept its place in the system. Once accepted, negative numbers revealed a beautiful symmetry in arithmetic. Every positive number has a negative counterpart, its mirror image across zero, its opposite in the sense that together they sum to nothing. This pairing gave zero a new significance, not merely as a placeholder or a starting point, but as the point of perfect balance between 2 infinite directions. The integers, all the whole numbers, positive and negative, with zero between them, extended infinitely in both directions along the number line, a complete and symmetric structure with zero at its still center. The rules governing arithmetic with negative numbers follow from this symmetry with quiet consistency. Adding a negative number is equivalent to subtracting a positive one. Subtracting a negative number is equivalent to adding a positive one, a double negation that returns to the forward direction. Multiplying 2 negative numbers produces a positive result, a rule that initially seems arbitrary but emerges necessarily from the requirement that the distributive property continue to hold across the expanded number system. The number line. The number line is the geography of mathematics. It is the image that gathers every number discussed so far, the counting numbers, zero, the negatives, the fractions, the decimals, and arranges them all into a single, continuous, infinitely extending picture. It transforms number from a purely abstract concept into something spatial, something that can be pointed to and traversed, something that has position and direction and distance. Of all the visual representations mathematics has ever produced, the number line is perhaps the most quietly profound. The construction of the number line begins with a single straight line extending infinitely in both directions. A point is chosen somewhere along it and labeled zero. This is the origin, the reference point from which all other positions are measured. To the right, the positive numbers extend outward in order, each whole number occupying its own point at a fixed and equal distance from its neighbors. To the left, the negative numbers mirror them exactly, descending in order away from zero with the same regularity. The line is not merely a list of numbers arranged horizontally. It is a map of numerical space where position encodes value and distance encodes difference. What makes the number line extraordinary is what lives between the whole numbers. The integers occupy their evenly spaced points, but between any two consecutive integers, the line is not empty, it is densely, almost impossibly, populated. Between 0 and 1, every fraction with a denominator of 2, 3, 4, and every larger integer finds its place. Every terminating decimal, every repeating decimal, every ratio of whole numbers settles onto a precise and unique location. The fractions alone fill the line with infinite density, packing themselves into every interval with inexhaustible thoroughness, and yet the line accommodates all of them without crowding because a line contains infinitely many points. The number line also gave arithmetic a geometric interpretation that deepened the understanding of every operation. Addition became movement to the right, subtraction became movement to the left. The distance between two numbers became the absolute value of their difference, a length that could be measured regardless of direction. Multiplication by a positive number became a stretching of the line, scaling distances outward from zero. Multiplication by a negative number became both a stretching and a reflection, flipping the direction as well as changing the scale. Operations that were once purely symbolic became visible, traceable, spatial. In education, the number line serves as the first bridge between arithmetic and geometry, the first moment where a student sees that numbers and space are not separate domains, but deeply related ones. In advanced mathematics, this relationship deepens considerably. The real number line becomes the foundation for the study of continuity and limits. It extends into two dimensions as the coordinate plane and into three as space itself. It generalizes further into abstract spaces of any number of dimensions, each one preserving the essential idea that position encodes value and distance encodes relationship. Place value. Place value is the architecture of numbers. It is the system that determines not just which digits are used to write a number, but what each digit means depending on where it stands. A digit does not carry a fixed value of its own. Its value is determined entirely by its position within the number it inhabits. The same symbol can represent a single unit, 100 units, or 1,000,000 units, depending solely on where it is placed. This positional principle is one of the most elegant and consequential ideas in the entire history of mathematics, and it is so deeply embedded in the way numbers are written today that it can be easy to forget it was ever an invention at all. Before positional systems existed, writing numbers was an unwieldy affair. Many ancient systems assigned fixed symbols to specific values and built numbers by combining those symbols additively. The Roman numeral system is the most familiar example of this approach. To write a large number required assembling a long string of symbols, each carrying its own fixed meaning. Calculation with such systems was laborious and slow. The symbols gave numbers a readable form, but they did not provide the structural efficiency needed to perform arithmetic quickly or to represent very large quantities without enormous strings of characters. The invention of a positional number system changed everything. In such a system, a small set of symbols, in the system used today, the 10 digits from 0 through 9, can represent any number, no matter how large or how small, through the power of position alone. The rightmost position in a whole number represents ones. The next position to the left represents tens. The next represents hundreds, then thousands, then 10,000s, each position worth 10 times the one to its right. A digit placed in the hundreds position does not mean itself. It means itself multiplied by 100. The number 347 is not simply 3, 4, and 7 placed side by side. It is 3 hundreds, 4 tens, and 7 ones combined into a single quantity through the logic of position. 0 plays an indispensable role in this system. Without 0 as a placeholder, positional notation collapses. The difference between 52 and 502 lies entirely in the 0 occupying the tens position of the second number, signaling that no tens are present while hundreds and ones are. Remove that 0 and the positional information is lost. 0 does not merely represent nothing. It holds a position open, preserving the meaning of every other digit in the number. The same positional logic extends rightward past the decimal point into fractions. With each position representing a power of 1/10 rather than a power of 10, it extends leftward without limit as numbers grow larger. It scales with perfect consistency from the smallest decimal to the largest integer, governed throughout by the same simple principle of position multiplied by power. Factors. Factors are the mathematics of what fits. They are the numbers that divide evenly into a given number, leaving nothing behind, producing a whole number result without remainder or residue. To find the factors of a number is to ask which numbers are its exact divisors, which ones fold cleanly into it, which ones are hiding inside it as components of its construction. Factors reveal the internal structure of a number, the way it is built, the relationships it carries quietly within itself that ordinary inspection does not immediately reveal. The concept of a factor is rooted in the same physical intuition as multiplication and division. 12 objects can be arranged into one row of 12, 2 rows of 6, 3 rows of 4, or 4 rows of 3. Each of these arrangements is exact and complete, with nothing left over and no gaps unfilled. The numbers that make these arrangements possible, 1, 2, 3, 4, 6, and 12, are the factors of 12. They are the values for which 12 divides without remainder. The dimensions of every perfect rectangle that 12 unit squares can form. Factors are not abstract properties imposed upon a number. They are discoveries about its geometry, its divisibility, its inner architecture. Every whole number greater than 1 has at least 2 factors, 1 and itself. These two are always present, always guaranteed. For some numbers, these are the only factors. 7 divides evenly by 1 and by 7, and by nothing else. 11, 13, 17. Each of these numbers resists every division except the two that are always available. These numbers, divisible only by 1 and themselves, are the prime numbers, and they represent the simplest possible factor structure a number can have. For other numbers, factors accumulate. 24 has 8 factors, 1, 2, 3, 4, 6, 8, 12, and 24 reflecting a rich internal structure built from repeated combinations of smaller components. Finding the factors of a number is the beginning of a deeper investigation called factorization, the process of breaking a number down into its prime components. Every whole number greater than 1 can be expressed as a product of prime numbers in exactly one way, a fact so fundamental it carries the name the fundamental theorem of arithmetic. The prime factorization of a number is its most basic description, its irreducible identity. 12 is 2 multiplied by 2 multiplied by 3, and no other combination of primes produces 12. This uniqueness is not a coincidence. It is a deep structural property of the integers, one that mathematicians have relied upon for thousands of years. Factors also lie at the heart of the greatest common factor, the largest value that divides evenly into 2 or more numbers simultaneously, and the least common multiple, the smallest value into which 2 or more numbers divide evenly. Both concepts appear wherever fractions are simplified, equations are solved, and patterns in sequences are identified. Multiples are the mathematics of repetition. They are the numbers produced when a given value is multiplied by the counting numbers in sequence, one after another, generating an infinite chain of results that extends forward without end. Where factors look inward, asking what smaller values are hidden inside a number, multiples look outward, asking what larger values a number can build. The two concepts are complementary perspectives on the same underlying relationship, mirror images of divisibility seen from opposite directions. The multiples of any number are simply that number scaled upward, step by step, through every natural number in succession. The multiples of 3 are 3, 6, 9, 12, 15, and so on, each one a landing point reached by taking another step of 3 along the number line. The multiples of 7 are 7, 14, 21, 28, each one separated from the last by an interval of exactly 7. These sequences have a rhythm to them, a regularity that makes them recognizable and predictable. Once the step size is known, every element of the sequence is determined. There are no surprises, no gaps, no deviations from the pattern. Multiples are among the most orderly structures in all of arithmetic. Every number is a multiple of each of its factors, and every factor of a number divides evenly into every one of its multiples. This reciprocal relationship is one of the most frequently used connections in elementary mathematics. Knowing the factors of a number tells you which stepping patterns will land on it. Knowing the multiples of a number tells you which larger values it will reach. Together, factors and multiples define a number's position in the web of divisibility relationships that connects all the integers to one another. One of the most useful ideas built directly from multiples is the least common multiple of 2 or more numbers, the smallest value that appears as a multiple of all of them simultaneously. The least common multiple of 4 and 6 is 12, because 12 is the first number reached by both the multiples of 4 and the multiples of 6. Finding it requires identifying where two stepping sequences first land on the same point, where two rhythms that began together fall into coincidence again after diverging. This intersection point is essential in arithmetic, wherever fractions with different denominators must be added or subtracted, because it provides the smallest common unit into which both denominators divide evenly. Multiples also reveal patterns that extend deep into number theory. The multiples of 2 are precisely the even numbers, an infinite sequence that alternates with the odd numbers in perfect regularity across the entire integer line. The multiples of 10 mark the positions of the place-value boundaries that give the decimal system its structure. The multiples of any prime number define exactly the integers that number divides, carving the integers into two infinite sets, those it reaches and those it does not. Prime numbers. Prime numbers are the atoms of arithmetic. They are the whole numbers greater than 1 that cannot be divided evenly by anything other than 1 and themselves. The numbers that resist every attempt at factorization, that stand irreducible and indivisible against all the operations that break other numbers apart. Every other whole number greater than 1 is built from primes assembled through multiplication from these fundamental units. In this sense, prime numbers are not merely a special category of number, they are the basic material from which the entire structure of the integers is constructed. The first few primes announce themselves quietly: 2, 3, 5, 7, 11, 13. Each one a number that divides by nothing but itself, and 1, each one resisting the neat internal arrangements that composite numbers permit. 2 is the only even prime, divisible by 2 by definition, but also equal to 2 itself, sitting at the precise boundary between the even and the prime in a way no other number can. Beyond 2, every prime is odd because every even number greater than 2 is divisible by 2 and therefore not prime. The primes thin out as numbers grow larger, appearing less frequently among the integers, separated by longer and longer gaps, and yet they never disappear entirely. They continue appearing, scattered and seemingly irregular as far as the number line extends. The proof that primes continue forever is one of the oldest and most elegant arguments in all of mathematics, attributed to the ancient Greek mathematician Euclid. Suppose, he argued, that there were a finite number of primes. Multiply them all together and add 1. The resulting number is either prime itself or divisible by some prime. But it cannot be divisible by any prime in the original list, because dividing it by any of them leaves a remainder of 1. This contradiction means the original assumption was wrong. There is no finite list of primes. They are infinite in number, and no matter how far along the number line one travels, more primes will always lie ahead. Despite their infinite abundance, the distribution of prime numbers follows no simple repeating pattern. They appear with an irregularity that has fascinated and frustrated mathematicians for millennia. The gaps between consecutive primes grow on average as numbers increase, but they do so without predictable rhythm, sometimes clustering unexpectedly close and sometimes separating by vast distances. The question of exactly how primes are distributed among the integers, how many primes lie below any given number, and where exactly they fall, led to the development of some of the deepest and most beautiful mathematics ever produced, including the Riemann hypothesis, which remains one of the greatest unsolved problems in all of mathematics to this day. Prime numbers also form the foundation of modern cryptography, the science of encoding and protecting information. The difficulty of factoring very large numbers back into their prime components is the basis of the encryption systems that secure digital communication across the entire modern world. Odd and even. Odd and even are the first great division of the integers. They are the classification that splits every whole number into one of exactly two categories, a binary partition so clean and complete that nothing falls between them and nothing falls outside them. Every integer without exception is either odd or even, and no integer is both. This perfect sorting into two infinite families is one of the simplest structural observations in all of mathematics, and yet it carries within it a surprising depth, connecting arithmetic to algebra, geometry, and the abstract study of mathematical structure. The definition is straightforward. An even number is any integer that divides exactly by 2, leaving no remainder. 2, 4, 6, 8, 10. These are the even numbers, each one reachable by counting in steps of 2 from 0, each one a multiple of 2 in the sequence that extends infinitely in both directions along the number line. An odd number is any integer that does not divide exactly by 2, leaving a remainder of 1, 1, 3, 5, 7, 9. These are the odd numbers, each one falling precisely between two consecutive even numbers, offset by exactly 1 unit from the nearest multiple of 2. The two families interleave perfectly, alternating without interruption across the entire integer line. Odd and even, and odd and even, a rhythm that never breaks and never repeats a pattern before its time. The behavior of odd and even numbers under arithmetic operations follows rules of remarkable consistency. The sum of two even numbers is always even. The sum of two odd numbers is always even. The sum of an odd and an even number is always odd. These rules hold without exception for any integers whatsoever, regardless of their size or sign. The product of two even numbers is always even. The product of two odd numbers is always odd. The product of an even and an odd number is always even. Each of these results follows directly from the definitions, provable in a few lines of algebra, and yet their consistency across all possible cases gives them the character of natural laws, reliable enough to be used as tools in broader mathematical arguments. Odd and even are among the earliest examples of what mathematicians call a parity argument, a form of reasoning that classifies objects into two categories and draws conclusions from which category a result must fall into. Parity arguments appear throughout number theory, combinatorics, and abstract algebra, used to prove results that might otherwise seem to require much more elaborate machinery. If a sum must be even, one of its parts is odd, the other part must also be odd. This simple logic, applied carefully, can resolve questions of genuine mathematical depth. In geometry, odd and even appear in the study of symmetry and tiling. In graph theory, they determine whether certain paths and circuits are possible. In abstract algebra, they prefigure the concept of modular arithmetic and the deeper study of equivalence classes. Percentages are the mathematics of proportion made universal. They are a way of expressing any quantity as a fraction of 100, a standardized scale that allows vastly different measurements to be compared on equal terms. Where fractions and decimals describe portions in their own varied forms, percentages translate every proportion into the same common language, making the relative size of things immediately legible regardless of the original quantities involved. A percentage does not just describe how much, it describes how much in relation to a whole, and it does so in a unit that every calculation, every comparison, and every intuition can immediately read. The word itself carries the meaning directly. Percent means per hundred, out of 100, for every 100. A percentage is simply the answer to the question of how many parts out of every 100 a given quantity represents. 50% is 50 out of every 100, 1/2 of any whole. 25% is 25 out of every 100, 1/4 of any whole. 100% is the whole itself, complete and entire, every part accounted for. The scale runs naturally from 0, representing nothing, to 100, representing everything, with every gradation between them available for use. Converting between percentages and their fractional or decimal equivalents is a matter of straightforward arithmetic. A percentage divided by 100 becomes a decimal. 40% becomes 0.4, representing the same proportion in the language of place value. A fraction multiplied by 100 becomes a percentage. 3/4 multiplied by 100 yields 75%. These translations preserve the underlying proportion exactly, moving it between three different notations without changing its value. Each form has its own strengths. Fractions communicate exact ratios most clearly. Decimals facilitate calculation most efficiently. Percentages communicate relative size most intuitively. Percentages are everywhere in daily life because proportional comparison is one of the most universal needs human beings have. A shop offering 30% off a price invites an immediate and intuitive grasp of the saving without requiring knowledge of the original price. An election result showing one candidate receiving 52% of the vote communicates a near equal contest, with greater immediacy than any raw number could. A scientific study reporting that a treatment was effective in 78% of cases allows comparison with other treatments measured by the same standard. The percentage translates raw quantity into relative standing, and relative standing is almost always what actually matters. Percentage change is one of the most frequently used and most frequently misunderstood applications of the concept. An increase of 50% followed by a decrease of 50% does not return a quantity to its original value. The decrease is calculated on the larger, increased value, making the reduction in absolute terms larger than the original increase. This asymmetry catches intuition off guard and rewards careful calculation over approximation. In finance, percentages govern interest rates, returns, and inflation. In science, they describe concentrations, efficiencies, and probabilities. In statistics, they translate raw data into comparable proportions. Ratios are the mathematics expresses how two quantities compare to one another, not in terms of their individual sizes, but in terms of their relative proportion. A ratio does not describe how much of something there is in any absolute sense. It describes how much of one thing there is for every certain amount of another. This shift from absolute measurement to relative comparison is subtle but profound, and it opens a dimension of mathematical description that neither addition nor subtraction nor any of the previous operations fully captures. The notation of a ratio is deliberately simple. Two quantities are placed side by side, separated by a colon, and read as one quantity to another. A ratio of 3 to 2 means that for every 3 of the first quantity, there are 2 of the second. It makes no claim about the actual values involved. A mixture containing 3 parts water and 2 parts concentrate has a ratio of 3 to 2 whether the total volume is 5 milliliters or 5,000 liters. The ratio describes the relationship between the parts, and that relationship remains fixed even as the actual quantities scale freely up or down. This scale independence is one of the most powerful properties of ratios. Two situations with identical ratios are structurally equivalent in the relevant sense, even if their actual measurements are entirely different. A map drawn at a ratio of 1 to 50,000 preserves the spatial relationships of the landscape it represents, regardless of the fact that every distance has been reduced by a factor of 50,000. A recipe specifying ingredients in fixed ratios produces the same result whether scaled for 2 people or 200, because the proportional relationships between the ingredients remain constant. The ratio is the invariant, the thing that is preserved across all the variations in scale. Ratios also carry a deep connection to fraction and division. A ratio of 3 to 2 is equivalent to the fraction 3 halves, which is equivalent to the decimal 1.5, which expresses how many times larger the first quantity is than the second. Every ratio can be converted into a single number this way: the quotient of one quantity divided by the other, a number that summarizes the relationship between them in the most compressed possible form. This connection means that ratios inherit all the properties and techniques of fractional arithmetic, including the ability to simplify by dividing both terms by their greatest common factor. In geometry, ratios describe the proportions of similar figures, the relationship between corresponding sides of triangles that share the same angles, and the constant relationships between a circle's circumference and diameter that produce the extraordinary number called pi. In music, ratios define the harmonic relationships between frequencies that the ear perceives as consonant or dissonant. In physics, ratios appear in every dimensionless constant that describes the fundamental structure of the universe. Proportions are the mathematics of equivalence between relationships, where a ratio describes how two quantities compare to one another. A proportion makes a further claim that two ratios are equal, that two separate comparisons produce the same relative standing, that the relationship between one pair of quantities mirrors exactly the relationship between another. A proportion is not merely a comparison. It is a statement of structural correspondence, an assertion that two different pairs of numbers drawn from different contexts or different scales are governed by the same underlying ratio. The form of a proportion is simple and ancient. Two ratios are set equal to one another, and the equality between them is the mathematical content. 3 is to 6 as 5 is to 10. The ratio between 3 and 6 is 1 to 2. The ratio between 5 and 10 is also 1 to 2. These two pairs of numbers, different in every absolute sense, share the same proportional relationship, and that shared relationship is what the proportion asserts. It is a statement not about the numbers themselves, but about the pattern they both instantiate. The practical power of proportions lies in their ability to find unknown quantities from known relationships. If 3 items cost a certain amount, and the price is proportional to the quantity, then the cost of any other number of items can be determined from a single calculation. This form of reasoning, setting up two equal ratios and solving for the missing value, is one of the oldest and most widely used techniques in applied mathematics. It appears in recipe scaling, map reading, currency conversion unit transformation, and the calculation of similar dimensions in architecture and engineering. The proportion is the engine of proportional reasoning, and proportional reasoning is one of the most transferable quantitative skills a mind can develop. Cross-multiplication is the most direct method for solving a proportion. When two fractions are equal, the product of each numerator with the opposite denominator must also be equal. This relationship, simple in its algebra but elegant in its logic, transforms a statement about equal ratios into a straightforward equation that can be solved for any unknown. The technique works because equality between fractions implies a specific multiplicative relationship between their components, one that cross-multiplication makes explicit and immediately usable. Proportions also underlie the concept of direct variation, the relationship in which two quantities grow and shrink together at a constant rate. When one quantity doubles, the other doubles. When one is halved, the other is halved. The ratio between them never changes, no matter how the individual values shift. This constant ratio is the proportionality constant, and it describes the precise nature of the relationship in a single number. Physics, chemistry, and economics are dense with directly proportional relationships, each one describable by a single constant that encodes the rate at which one quantity responds to changes in another. Rounding is the mathematics of approximation. It is the process of replacing an exact value with a nearby value that is simpler, cleaner, and easier to work with, while remaining close enough to the original that the difference is either negligible or acceptable for the purpose at hand. Rounding does not seek perfect precision. It seeks useful precision, the level of detail that serves the task without burdening the calculation or the communication with unnecessary complexity. It is, in this sense, one of the most practical and most human of all mathematical operations, a deliberate and principled act of letting go. The mechanics of rounding rest on the concept of the nearest value within a chosen level of precision. To round a number to the nearest 10, one identifies which multiple of 10 the number sits closest to and replaces the original with that multiple. The number 43 rounds to 40 because 43 is closer to 40 than to 50. The number 47 rounds to 50 because 47 is closer to 50 than to 40. The number 45 sits exactly halfway between, and by the most widely used convention, it rounds upward to 50, the higher of the two candidates. This midpoint rule is a convention rather than a mathematical necessity, but it is consistent and universal, producing predictable results across every application. The same logic extends to any level of precision. A number can be rounded to the nearest whole number, the nearest tenth, the nearest hundredth, the nearest thousand, or any other place value position. The question is always the same: which of the two neighboring values at the chosen level of precision is the number closest to, and the answer always follows the same principle. Digits beyond the chosen precision are examined, and the retained digits are adjusted or preserved accordingly. The process is always local, always focused on the digit immediately beyond the boundary of the desired precision, and always governed by whether that digit is less than 5, equal to 5, or greater than 5. Rounding introduces the concept of rounding error, the small but real difference between a rounded value and the exact value it replaces in a single calculation. Rounding error is usually trivial. Across many successive calculations, it can accumulate into a discrepancy large enough to matter. Scientists, engineers, and financial analysts are trained to be aware of when rounding errors compound and when the accumulated imprecision of approximation begins to affect the reliability of results. This awareness, knowing not just how to round, but when rounding is safe and when it demands caution, is one of the subtler skills of quantitative reasoning. In everyday life, rounding makes communication efficient and natural. Populations are rounded to the nearest thousand. Prices are rounded to the nearest unit of currency. Distances are rounded to the nearest mile or kilometer. Measurements are rounded to the precision that instruments can reliably provide. Estimation. Estimation is the mathematics of intelligent approximation. It is the art of arriving at an answer that is close enough to be useful without performing the full calculation that an exact answer would require. Where rounding takes a precise value and simplifies it, estimation works in the opposite direction, building a rough but reasonable answer from incomplete information, from rounded inputs, from order of magnitude thinking, from a confident and calibrated sense of scale. Estimation is not guessing. It is disciplined, structured, and governed by mathematical reasoning, even when it does not produce an exact result. The simplest form of estimation involves replacing exact values with convenient approximations before calculating. A grocery bill totaling items priced at $2.87, $4.12, and $6.93 can be estimated quickly by rounding each item to the nearest dollar and adding 3, 4, and 7 to produce 14. The exact total will be close to $14, and knowing this before reaching the register requires no paper, no calculator, and no laborious arithmetic. The estimate is not a substitute for the exact answer in every context, but in many contexts, knowing the approximate magnitude is entirely sufficient. Fermi estimation takes this principle further, applying it to questions where exact data is unavailable or impractical to obtain. Named after the physicist Enrico Fermi, who was famous for his ability to produce surprisingly accurate estimates of seemingly impossible quantities, this approach breaks a complex question into simpler components, estimates each component from basic knowledge and reasonable assumptions, and combines them to produce an overall estimate. How many piano tuners work in a large city? How many heartbeats occur in a human lifetime? How many molecules of air are in a room? Each of these questions yields to careful decomposition and confident approximation, arriving at an answer that may be imprecise but is firmly in the right range. The skill of estimation is inseparable from a feel for order of magnitude. The sense of how large something is in terms of powers of 10. Is the answer closer to 100 or 1,000? Is a proposed measurement closer to a millimeter or a centimeter? These are order of magnitude judgments, and they serve as sanity checks against errors in calculation and errors in assumption. A scientist who calculates the mass of an object and arrives at a result 12 orders of magnitude larger than expected knows immediately that something has gone wrong without needing to verify every step. The estimate provides the boundary within which the exact answer must reasonably fall. Estimation also teaches a valuable epistemic lesson. Not every question requires an exact answer, and the pursuit of false precision, decimal places carried far beyond the accuracy of the underlying data, is itself a form of mathematical error. Knowing when to estimate and when to calculate exactly is a judgment that grows with mathematical maturity. Order of operations. Order of operations is the grammar of arithmetic. It is the set of rules that determines the sequence in which the operations within a mathematical expression are performed, ensuring that any expression, however complex, produces exactly one unambiguous result, regardless of who evaluates it or how they approach it. Without a shared order of operations, the same string of symbols could yield different answers depending on where a reader chose to begin, turning mathematics from a universal language into an inconsistent one. The order of operations is what prevents that ambiguity, transforming a collection of numbers and symbols into a statement with a single determinate meaning. The need for such rules becomes immediately apparent in any expression involving more than one operation. Consider the expression 2 plus 3 multiplied by 4. If the addition is performed first, the result is 5 multiplied by 4, which is 20. If the multiplication is performed first, the result is 2 plus 12, which is 14. The same symbols, the same numbers, the same operations, yet two entirely different answers, depending solely on the sequence of evaluation. Mathematics cannot tolerate this ambiguity. A universal agreement about which operation takes precedence is not merely convenient, it is essential. The agreed hierarchy places certain operations above others in a fixed priority sequence. Expressions inside parentheses are evaluated first because parentheses are the explicit instruction to override the default sequence, to perform something before everything else, regardless of what that something is. After parentheses come exponents, the operations of repeated multiplication that grow numbers rapidly and whose compact notation demands early resolution. After exponents come multiplication and division, which hold equal priority to one another and are performed in sequence from left to right across the expression. Finally come addition and subtraction, also equal in priority, also resolve from left to right after everything above them has been evaluated. Parentheses are the most powerful tool within this system precisely because they override everything else. Any part of an expression enclosed in parentheses is resolved first, regardless of which operations it contains. Nested parentheses, parentheses within parentheses, are resolved from the innermost set outward, each layer peeling away to reveal the simplified value it contains before the surrounding expression proceeds. This nesting capacity means that parentheses can impose any desired sequence on any expression, making the default hierarchy a starting point rather than a constraint. The mnemonic devices invented to help students remember the hierarchy, phrases whose initials correspond to the sequence of operations, have become familiar fixtures of mathematics education across many cultures and languages. They serve their purpose well, providing a memorable shorthand for a rule that must become automatic with practice. In algebra, the order of operations governs the evaluation and simplification of every expression. In computer programming, the same hierarchy is built directly into every language, determining how expressions are passed and evaluated by machines processing millions of calculations per second. Exponents. Exponents are the mathematics of repeated multiplication. They are the notation that compresses a long chain of identical multiplicative steps into a single compact expression, just as multiplication compressed repeated addition. Where multiplication asks how many times a number is added to itself, an exponent asks how many times a number is multiplied by itself, and the results grow with a speed and scale that ordinary arithmetic does not prepare the mind to expect. Exponents are where numbers begin to behave in ways that feel almost extravagant, reaching magnitudes that strain intuition and reveal the true meaning of the word large. The notation is economical and precise. A base number is written at normal size, and a smaller number, the exponent, is placed above and to its right. 2 raised to the power of 3 means 2 multiplied by itself 3 times, producing 8. 10 raised to the power of 6 means 10 multiplied by itself 6 times, producing 1,000,000. The base is the value being multiplied, and the exponent is the count of how many times that multiplication is performed. Together they encode an enormous amount of information in an extraordinarily small space, and they do so with perfect clarity. The growth produced by exponentiation is qualitatively different from the growth produced by addition or multiplication. Adding 10 to a number increases it by a fixed amount. Multiplying a number by 10 increases it by a fixed factor. But raising 10 to successively higher powers produces results that themselves grow by larger and larger factors with each step. 10 to the first is 10, 10 to the second is 100. 10 to the third is 1,000, 10 to the sixth is 1,000,000, 10 to the 12th is 1,000,000,000. Each additional unit of exponent multiplies the result by 10 again, so the gap between consecutive powers grows as rapidly as the powers themselves. This behavior, called exponential growth, is one of the most consequential mathematical patterns in the natural world. Exponents also extend naturally beyond the counting numbers into territory that initially seems paradoxical. Any number raised to the power of 0 is 1, a result that follows necessarily from the patterns of exponent arithmetic, even though multiplying something by itself 0 times seems to defy intuition. Negative exponents produce reciprocals, placing the base in the denominator of a fraction and representing quantities smaller than 1. Fractional exponents connect exponentiation to roots, with 1/2 as an exponent producing the square root and 1/3 producing the cube root. Each of these extensions follows inevitably from the internal logic of the operation, requiring no special exceptions and no separate rules. In science, exponential notation allows the almost incomprehensibly large and the almost incomprehensibly small to be written compactly and compared directly. The mass of the sun and the mass of a proton, the distance between galaxies and the diameter of an atomic nucleus all find their natural expression in the language of exponents, square roots. Square roots are the mathematics of undoing multiplication by itself. They are the operation that asks for any given number, which value multiplied by itself produces that number. Where squaring a number means multiplying it by itself to produce a result, the square root reverses that process entirely, working backward from the result to recover the original value. The square root is the inverse of squaring in the same deep sense that subtraction is the inverse of addition and division is the inverse of multiplication. It completes the relationship, closes the loop, and asks the question that squaring leaves open. The concept has a natural geometric origin that makes its name immediately meaningful. If a square has an area of 9 square units, then each of its sides has a length of 3 units, because 3 multiplied by 3 is 9. The square root of 9 is 3. And it is the length of the side of a square with that area. This geometric interpretation gives square roots a tangible presence that pure arithmetic does not always provide. A square root is not merely a number produced by a calculation. It is a length, a dimension, a spatial quantity recoverable from an area. The connection between the operation and the shape it is named for is not incidental, but foundational. The square roots of perfect squares, numbers like 1, 4, 9, 16, 25, and 36, each of which is the product of a whole number multiplied by itself, are themselves whole numbers, clean and exact. The square root of 16 is 4. The square root of 100 is 10. These results sit comfortably within the familiar number system, requiring no extension or elaboration. But the square roots of numbers that are not perfect squares behave very differently, and their behavior prompted one of the most significant expansions in the history of mathematics. The square root of 2 is not a whole number. It is not a fraction. It is not a ratio of any two whole numbers whatsoever. When the ancient Greek mathematicians first proved this, the discovery was deeply unsettling, because it revealed that the number line contained values that the rational numbers, all the fractions, could not reach. The square root of 2 falls between 1 and 2, closer to 1.4, but it cannot be expressed as any exact fraction, no matter how large the numerator and denominator. Its decimal expansion continues without end and without any repeating pattern. It is irrational, a member of a family of numbers that populate the gaps left by the rationals in the number line. The set of irrational numbers discovered through square roots expanded the number system from the rationals to the reals, encompassing every point on the continuous number line. This expansion was not merely technical. It was a revelation about the nature of continuity itself. In geometry, physics, and engineering, square roots appear wherever areas are converted to lengths, wherever distances are calculated in 2 or 3 dimensions, and wherever circular and triangular relationships are precisely described. Absolute value is the mathematics of pure distance. It is the operation that strips a number of its sign, discarding the information about direction and retaining only the information about magnitude, returning how far a value lies from 0 without any regard for which side of 0 it falls on. The absolute value of 3 is 3. The absolute value of -3 is also 3. Both numbers are the same distance from 0, separated from it by exactly 3 units, and absolute value recognizes that distance as the only thing that matters, setting aside the distinction between positive and negative as irrelevant to the question being asked. The notation is clean and immediate. 2 vertical bars enclose the number or expression, and the result is always non-negative. The absolute value of any positive number is itself unchanged, because a positive number is already a distance measured in the forward direction from 0. The absolute value of any negative number is its positive counterpart, because negating the sign recovers the distance without the direction. The absolute value of 0 is 0, because 0 is already at the reference point, separated from itself by no distance at all. These 3 cases exhaust all possibilities, and together they define the operation completely. The geometric interpretation of absolute value is its most natural and illuminating description. On the number line, absolute value is simply distance from the origin, not displacement, which carries direction, but distance, which does not. This distinction mirrors the earlier distinction between distance and displacement in measurement. A point located at -7 is 7 units from 0, and a point located at +7 is also 7 units from 0. Absolute value collapses the directional information and returns the length of the gap between the point and the origin, the same regardless of which side the point lies on. This interpretation extends naturally to the distance between any two numbers, not just between a number and 0. The distance between 5 and -3 is the absolute value of their difference, which is the absolute value of 8, which is 8. The absolute value of the difference between two numbers measures how far apart they lie on the number line, without any concern for which is larger or which direction the gap runs. This formula for distance appears throughout algebra, analysis, and geometry, providing a consistent and direction-independent measure of separation. Absolute value also appears naturally in situations where only the size of a deviation matters, not its direction. In statistics, absolute deviations measure how far individual data points stray from a central value. In physics, absolute values appear wherever magnitudes of forces, speeds, or field strengths are needed without directional qualification. In error analysis, the absolute value of the difference between a measured and a true value gives the magnitude of the measurement error, the size of the discrepancy regardless of whether the measurement fell above or below the truth. Variables. Variables are the mathematics of the unknown and the general. They are the symbols, most commonly letters, that stand in place of numbers whose values are either not yet determined, not fixed, or intended to represent any number from a particular set. A variable is a placeholder that holds a space open in a mathematical expression, a blank waiting to be filled, a name given to a quantity whose specific value may be found, may vary, or may simply remain unspecified because the statement being made is meant to hold for all possible values rather than any particular one. Variables are where arithmetic ends and algebra begins. The leap from arithmetic to algebra is precisely the leap from working with specific numbers to working with numbers in general. Arithmetic asks what is 3 plus 4. Algebra asks what is any number plus 4, or what number, when 4 is added to it, produces a given result. This generalization is achieved entirely through the introduction of variables. A single letter, placed where a specific number would otherwise stand, transforms a particular calculation into a universal statement, a claim not about one instance but about every instance of a particular form. The equation expressing that any number added to itself produces twice that number holds for every number simultaneously, because the variable represents all of them at once. Variables serve two distinct purposes that are worth distinguishing clearly. In an equation, a variable typically represents a specific unknown value that the equation constrains and that the process of solving is meant to discover. The equation says that a certain quantity, when operated on in a specified way, produces a specified result, and the variable names that quantity. Solving the equation means finding which value or values the variable must take for the equation to hold. In a formula or identity, a variable plays a different role. It represents any value from some set, and the formula expresses a relationship that holds for all of them. The area of a rectangle equals its length multiplied by its width. This statement holds for every possible rectangle. And the variables are not unknowns to be solved, but placeholders expressing generality. The choice of letters for variables is partly conventional and partly meaningful. Single letters from the middle of the alphabet, particularly X, Y, and Z, are conventional choices for unknowns. Letters from the beginning of the alphabet often represent constants or parameters that are fixed for a given problem, but variable across problems. Letters like N and K often signal that the variable is expected to take only whole number values. These conventions are not rules, but shared habits accumulated over centuries of mathematical practice, making expressions easier to read for anyone familiar with the tradition. Variables also introduced mathematics to the idea of expression, of combining letters and numbers through operations to form structures that can be manipulated, simplified, and transformed according to consistent rules without ever knowing the specific value the letter represents. Expressions. Expressions are the phrases of mathematics. They are combinations of numbers, variables, and operations that represent a quantity, a value, or a relationship, assembled according to the rules of mathematical grammar into a coherent and meaningful whole. An expression does not make a claim. It does not assert that two things are equal or that one is greater than another. It simply represents something, standing for a value the way a noun phrase stands for a thing, complete in itself without requiring a verb to give it meaning. This distinction between an expression and a statement is one of the first and most important organizational principles in algebra. The simplest expressions are the ones already familiar from arithmetic. A single number is an expression. A single variable is an expression. 3 multiplied by 5 is an expression, one whose value can be immediately calculated. But expressions become genuinely interesting when they combine numbers and variables through multiple operations into structures whose value depends on what the variable represents. 3 multiplied by x plus 7 is an expression that takes a different value for every value of x, collapsing to a specific number, only when x is assigned 1. The expression encodes a process, a recipe for producing a number from an input without specifying what that input is. The components of an expression have names that reflect their structural roles. A term is any part of an expression that is separated from other parts by addition or subtraction. In the expression 5x squared plus 3x minus 2, there are 3 terms, each one a product of constants and variables. A coefficient is the numerical factor multiplying a variable within a term. In the term 3x, the coefficient is 3, indicating how many groups of x are present. A constant term is a term containing no variable, a fixed numerical value that contributes to the expression without depending on any input. The degree of an expression is the highest exponent appearing on any variable, a measure of its complexity and its behavior under various operations. Simplifying an expression means reducing it to its most compact and readable form without changing its value. Like terms sharing the same variable raised to the same power can be combined by adding their coefficients. 3x and 5x are like terms whose sum is 8x. Unlike terms cannot be combined this way. 3x and 5x squared are unlike terms that must remain separate. The process of identifying and combining like terms is one of the foundational manipulations of algebra, and it appears in virtually every algebraic calculation regardless of complexity. Expressions can be evaluated, substituted into, expanded, factored, and transformed. They are the raw material of algebra, the objects upon which every algebraic operation acts. Equations are built from expressions. Functions are defined by expressions. Every formula in science, engineering, And mathematics is an expression assigned to represent a quantity of interest. Equations are the sentences of mathematics, where expressions are phrases representing quantities without making claims. Equations bring two expressions together and assert that they are equal, that the value on the left side of an equal sign and the value on the right side are one and the same. This assertion of equality is the fundamental act of mathematical statement making, the moment where mathematics moves from description to declaration, from representing a quantity to making a claim about the relationship between quantities. Equations are where the language of mathematics becomes genuinely propositional, capable of being true or false, capable of constraining the unknown, capable of being solved. The equal sign itself carries enormous weight in this structure. It does not mean produces or results in or leads to, though it is sometimes read that way in casual use. It asserts identity of value, a symmetrical and complete equivalence between the two expressions it connects. Whatever transformations are applied to an equation, the equal sign must be preserved and honored. Both sides must remain equal throughout every step of manipulation. This requirement that any operation applied to one side must be applied equally to the other is the central discipline of algebraic solving, the rule that keeps the balance maintained as the equation is progressively simplified toward a solution. Solving an equation means finding the value or values of the variable that make the equation true, that satisfy the equality it asserts. The process is guided by the goal of isolating the variable on one side, surrounding it with nothing but its own value. Addition and subtraction move constant terms from one side to the other. Multiplication and division remove coefficients from variables. Each step is an application of a legal transformation, one that preserves the equality while bringing the variable closer to isolation. When the variable stands alone, its value is revealed and the equation has been solved. Not all equations behave the same way. A linear equation containing the variable only to the first power produces exactly one solution in most cases, a single value that satisfies the equality. A quadratic equation containing the variable squared can produce two solutions, one solution, or no real solutions depending on the specific values involved. Higher degree equations can have more solutions still, and some equations have infinitely many solutions, holding true for every value of the variable simultaneously. These are the identities, expressions of universal truth about mathematical relationships that hold regardless of what the variable represents. Equations also describe relationships between quantities that change together. The equation describing a line expresses how two variables are linked by a constant proportional relationship. The equations of physics express how forces, masses, energies, and motions are constrained by the laws of nature. Every scientific formula is an equation, asserting that one way of measuring a quantity equals another, that the universe honors a particular relationship without exception. Inequalities. Inequalities are the mathematics of comparison without equality. They are the statements that describe the relationship between two quantities when those quantities are not the same, when one is larger or smaller than the other, when the balance that equations assert is deliberately and meaningfully absent. Where an equation draws a precise line between two expressions and declares them identical, an inequality describes a range, a region, a set of possibilities rather than a single determined value. Inequalities are not weaker than equations. They are differently powerful, capable of capturing a kind of mathematical truth that equations cannot express. The symbols of inequality are few and immediately readable. The less than symbol points toward the smaller quantity. The greater than symbol points toward the larger. Less than or equal to and greater than or equal to add the boundary value to the comparison, including the point of equality within the range being described. These four symbols, combined with the same expressions that populate equations, produce statements of enormous variety and applicability. A temperature greater than 0 describes every value on an infinite ray extending from 0 in the positive direction. A number between 3 and 7 describes every value within a bounded interval, the entire continuous stretch of the number line between those two endpoints. Solving an inequality follows the same general logic as solving an equation, with one critical and consequential difference. When both sides of an inequality are multiplied or divided by a negative number, the direction of the inequality reverses. This rule has no counterpart in equation solving and must be observed with care. It arises from the way the number line orients itself. Multiplying every number by -1 reflects the entire line across 0. swapping the positions of values greater than 0 with values less than 0 and reversing every ordering relationship in the process. Failing to flip the inequality symbol when this reflection occurs produces a solution set pointing in entirely the wrong direction. The solution to an inequality is not a single value, but a set of values, typically expressed as an interval or a union of intervals on the number line. This solution set represents every value the variable could take while keeping the inequality true. Graphically, it appears not as a single point but as a shaded region, a continuous stretch of the number line indicating the full range of solutions. When two inequalities are combined into a system, the solution set is the overlap of their individual solution sets, the region where both are simultaneously satisfied. Inequalities appear throughout mathematics and its applications wherever constraints, bounds, and ranges are more natural than exact values. In optimization, inequalities define the feasible region within which a solution must be found. In analysis, inequalities establish the bounds that proofs require. In statistics, inequalities describe confidence intervals and tolerance ranges. In everyday life, inequalities govern budgets, safety thresholds, and acceptable margins of error. Functions are the mathematics of dependable relationship. They are the formal structure that captures the idea of one quantity depending on another, of an output being determined reliably and unambiguously by an input, of a rule that transforms every value it receives into exactly one corresponding result. A function is not merely a formula or an equation or a graph, though it can be expressed as any of these. It is the underlying relationship itself, the dependable correspondence between inputs and outputs that those representations describe. Functions are arguably the single most important concept in all of mathematics, the idea around which the entire discipline organizes itself at every level of sophistication. The defining property of a function is its reliability. For every input provided, there is exactly one output produced, not sometimes one and sometimes two. Not one output for most inputs and none for others. Exactly one, always, for every input in the collection, the function is defined upon. This property, known as the vertical line test when functions are viewed as graphs, is what distinguishes a function from a more general relationship between quantities. A relationship that assigns two different outputs to the same input is not a function. The reliability of the single output is the essential feature, the guarantee that makes functions useful as models of deterministic processes. The language of functions is built around a small set of terms that carry precise meanings. The domain is the complete collection of inputs the function accepts, every value for which the rule produces a defined and valid output. The range is the complete collection of outputs the function actually produces, every value that results from applying the rule to some input in the domain. The rule itself, the process that transforms each input into its corresponding output, is expressed in whatever form is most natural for the function at hand, as a formula, a table, a graph, or a verbal description. A function is fully described when its domain and its rule are both clearly specified. The notation developed for functions is economical and expressive. Writing f of x means the output produced by the function named f when the input is x. This notation separates the name of the function from the name of the input, allowing the same function to be evaluated at different inputs without confusion. It also makes the dependency explicit and visible, announcing immediately that the output depends on the input in the specific way the function defines. Functions appear wherever one quantity determines another in a consistent and predictable way. The position of a falling object depends on the time elapsed. The revenue of a business depends on the number of units sold. The temperature at a location depends on the season and the latitude. In each case, the dependency is the function, and the function is the precise mathematical description of how the determining quantity produces the determined one. Coordinate geometry. Coordinate geometry is the mathematics of location made algebraic. It is the system that assigns every point in space a pair of numbers, and in doing so creates a bridge between the visual world of shapes and the symbolic world of equations. Before coordinate geometry, algebra and geometry existed as largely separate disciplines, each with its own methods, its own language, and its own questions. Coordinate geometry united them, revealing that every geometric shape could be described by an equation, and every equation could be visualized as a shape. It is one of the most powerful unifications in the history of mathematics, and it emerged from a remarkably simple idea. The foundation of the system is the coordinate plane, constructed from two number lines placed perpendicular to one another, crossing at their shared 0 point, the origin. The horizontal line is called the x-axis, and it measures position in the left-right direction. The vertical line is called the y-axis, and it measures position in the up-down direction. Together, they divide the plane into 4 quadrants, filling every point of an infinite flat space with a unique address expressed as an ordered pair of numbers. The first number in the pair, the x-coordinate, specifies how far the point lies horizontally from the origin. The second number, the y-coordinate, specifies how far it lies vertically. Every point in the plane has exactly one such pair, and every such pair corresponds to exactly one point. This correspondence between points and number pairs is the engine of coordinate geometry. Once a point has coordinates, it can be reasoned about algebraically. The distance between 2 points becomes a calculation using the Pythagorean theorem applied to their coordinate differences, a formula that converts a geometric measurement into an arithmetic one. The midpoint of a segment becomes the average of the coordinates of its endpoints. A simple and elegant expression of the geometric concept of center in algebraic terms, geometric properties become algebraic conditions, and algebraic conditions become geometric shapes, each domain illuminating the other through this shared language of coordinates. The most immediate demonstration of this power is the straight line. A straight line in the coordinate plane is not merely a visual object, but a precise algebraic relationship between the x and y coordinates of every point it contains. Every point on a given line satisfies a specific equation, and every point that satisfies that equation lies on the line. The line and the equation are the same object described in 2 different languages, and the coordinate system is the dictionary that translates between them. Circles, parabolas, ellipses, and hyperbolas all yield similarly to coordinate description, each revealing its geometric identity through the algebraic form of its equation. In 3 dimensions, the system extends naturally to ordered triples, locating every point in space with 3 coordinates and allowing surfaces and volumes to be described algebraically. Slope. Slope is the mathematics of steepness. It is the measure of how steeply a line rises or falls as it moves across the coordinate plane. The numerical description of inclination that captures in a single value everything about the direction and rate of change that a straight line expresses. Slope answers a precise and fundamental question about every line in the plane. For every unit moved horizontally, how much does the line move vertically? And the answer to that question, a single ratio of vertical change to horizontal change, is the slope. Simple in its definition, profound in its reach, slope is one of the most frequently appearing and most conceptually significant numbers in all of mathematics. The calculation of slope follows directly from its definition. Given any 2 points on a line, the slope is found by dividing the difference in their vertical coordinates by the difference in their horizontal coordinates. The vertical difference is how much the line rises or falls between the 2 points. The horizontal difference is how far it travels sideways. Their ratio is the rate of that rise or fall, expressing it not in absolute terms, but relative to horizontal progress. This ratio is the same for any 2 points chosen on the same straight line, a constancy that is itself a defining property of straightness. A curve, by contrast, has a different slope at every point, changing as the direction of the curve changes. A positive slope describes a line that rises from left to right, climbing upward as horizontal position increases. The larger the positive slope, the steeper the rise. A negative slope describes a line that falls from left to right, descending as horizontal position increases. A slope of 0 describes a perfectly horizontal line, one that neither rises nor falls regardless of horizontal position. An undefined slope belongs to a perfectly vertical line, one that rises infinitely steeply, where horizontal position never changes and the ratio of vertical to horizontal change cannot be computed. Slope also carries meaning as a rate of change, and this interpretation extends far beyond the geometry of lines. Whenever 2 quantities are related linearly, the slope of the line describing their relationship is the rate at which one quantity changes per unit of change in the other. The slope of a distance time graph is speed, the rate at which distance increases with time. The slope of a cost quantity graph is unit cost, the rate at which expense grows with each additional unit. This interpretation makes slope one of the foundational ideas connecting algebra to the sciences, economics, and every domain where rates of change matter. The concept of slope also prepares the mind for one of the central ideas of calculus. The derivative, the instantaneous rate of change of a function at a single point, is defined precisely as the slope of the line that best approximates the function at that point, found by taking the limit of slope calculations over smaller and smaller intervals. Linear equations are the mathematics of straight relationships. They are the equations that describe proportional, constant rate connections between variables, producing lines when graphed in the coordinate plane and expressing the simplest and most fundamental form of algebraic dependence. A linear equation contains no exponents beyond 1, no variables multiplied together, no curves or bends in its graphical expression. It moves with perfect uniformity from any point to any other, changing at the same rate throughout its entire extent. This constancy of rate is both its defining characteristic and the source of its extraordinary usefulness across mathematics and its applications. The standard forms for expressing linear equations each emphasize a different aspect of the line they describe. The slope-intercept form, perhaps the most immediately readable, writes the equation as the output variable equal to the slope multiplied by the input variable plus a constant. The slope tells how steeply the line rises or falls. The constant, called the y-intercept, tells where the line crosses the vertical axis, the value of the output when the input is 0. Together, these two numbers completely characterize the line, specifying its direction and its position in the plane with no ambiguity. Given the slope and the intercept, the line is fully determined. The point-slope form approaches the same line from a different starting point, useful when the slope is known, but the intercept is not immediately available. If the slope of a line and the coordinates of one point it passes through are both known, the equation can be written directly from those two pieces of information. The standard form, which places both variables on the same side of the equation with a constant on the other, is useful in certain algebraic contexts and emphasizes the symmetric relationship between the two variables, rather than treating one as determined by the other. The process of solving a linear equation in one variable is the most direct application of algebraic manipulation. Each step isolates the variable further, moving constants to one side through addition or subtraction and removing coefficients through multiplication or division until the variable stands alone with its value revealed. This process always terminates in exactly one solution for a genuine linear equation, a single value that satisfies the equality, reflecting the geometric fact that a non-Hausstorian line crosses any horizontal level at exactly one point. Linear equations appear wherever one quantity changes at a constant rate relative to another. Distance traveled at constant speed, the accumulation of savings at a fixed rate, temperature change at a steady pace, all of these produce linear relationships between the quantities involved. The equation captures that relationship in compact algebraic form, allowing every value of one quantity to be immediately determined from the value of the other. In physics, economics, engineering, and data analysis, linear equations serve as the first and most natural model for relationships between quantities. More complex relationships are often understood as departures from linearity, measured by how far they deviate from the straight and uniform behavior that linear equations describe. Systems of equations. Systems of equations are the mathematics of simultaneous constraint. They are collections of two or more equations considered together, each one placing its own condition on the same set of variables, all of them active at once, all of them demanding satisfaction at the same time. Where a single equation constrains one relationship between quantities, a system of equations constrains multiple relationships simultaneously, narrowing the space of possible solutions from the broad range permitted by any one equation alone to the specific values where every equation in the collection is satisfied together. A system of equations is not merely several equations placed side by side. It is a set of conditions that must all hold at once, and the solution is the point where every condition converges. The geometric interpretation of a system of two linear equations in two variables makes the concept immediately visual. Each equation describes a straight line in the coordinate plane, and the solution to the system is the point where those lines intersect, the single location that lies on both lines simultaneously. If the lines cross at one point, the system has exactly one solution: the coordinates of that intersection. If the lines are parallel, never meeting regardless of how far they extend, the system has no solution because no point can lie on both lines at once. If the lines are identical, every point on one is also on the other, and the system has infinitely many solutions, an entire line's worth of values, satisfying both equations simultaneously. The algebraic methods for solving systems of equations translate this geometric picture into precise calculation. The substitution method solves one equation for one variable and substitutes the resulting expression into the other equation, reducing the system to a single equation in a single variable. The elimination method adds or subtracts multiples of the equations from one another, chosen to cancel one variable and leave an equation containing only the other. Both methods are systematic and reliable, guaranteed to find the solution when one exists or to reveal its absence when it does not. Systems of equations are not limited to two equations or two variables. A system of three equations in three variables corresponds geometrically to three planes in three-dimensional space, and the solution is the point where all three planes intersect. Larger systems, with many equations and many variables, arise naturally in science, economics, and engineering, where complex situations are modeled by networks of interrelated constraints. Solving large systems efficiently requires techniques from linear algebra, particularly the method of matrix row reduction, which extends the elimination approach to any number of equations and variables through systematic and organized steps. In everyday applications, systems of equations model situations where multiple conditions must be satisfied at once, mixing solutions to achieve a target concentration, allocating resources across competing needs, finding prices that balance supply and demand. Each of these requires satisfying several constraints simultaneously, and each yields naturally to the structure of a system of equations. Polynomials are the architecture of algebraic expressions. They are the expressions built from variables and constants combined through addition, subtraction, and multiplication, with variables raised only to whole number powers, assembled into a structured sum of terms that grows in complexity and richness as more terms are added. A polynomial does not contain variables in denominators, does not involve fractional or negative exponents, does not include roots of variables in unresolved form. It is a clean, well-behaved algebraic object constrained by these boundaries into a family of expressions that is broad enough to describe an enormous variety of mathematical situations and regular enough to be studied with powerful and elegant tools. The simplest polynomials are already familiar. A constant is a polynomial of degree 0, a single term containing no variable. A linear expression is a polynomial of degree 1 containing a variable to the first power and perhaps a constant term. A quadratic expression is a polynomial of degree 2, its highest term containing the variable squared. A cubic contains the variable cubed. Each step up in degree adds a new layer of complexity to the shape the polynomial traces when graphed, and a new tier of behavior to the mathematical questions it raises. The degree of a polynomial is its most fundamental descriptor, governing how many solutions its corresponding equation can have, how many turns its graph can make, and which algebraic techniques apply to it. The terms of a polynomial are arranged by convention in descending order of degree, the highest power first and the lowest last, with the constant term at the end. This ordering is not arbitrary but practical, making the degree immediately visible at the start of the expression and organizing the terms in a way that simplifies addition, subtraction, and multiplication. Adding two polynomials means combining like terms, pairing each term with the term of matching degree in the other polynomial, and summing their coefficients. Multiplying two polynomials requires distributing every term of one across every term of the other, then collecting and combining the resulting terms by degree, a process that scales in effort with the number of terms but follows the same distributive logic throughout. Polynomials possess a smoothness and regularity that makes them uniquely tractable. Their graphs are continuous curves without breaks, jumps, or vertical asymptotes. They can be differentiated and integrated at every point. They can be evaluated at any real number. One of the most powerful results in all of mathematics, the Weierstrass approximation theorem, establishes that any continuous function on a closed interval can be approximated to any desired level of accuracy by a polynomial, making polynomials the universal approximators of smooth mathematical behavior. Factoring polynomials, finding the simpler polynomial expressions whose product reconstructs the original, connects them deeply to the theory of roots and the geometry of their graphs. The roots of a polynomial, the input values that produce an output of 0, are the points where its graph crosses the horizontal axis, the solutions to the corresponding polynomial equation. Factoring. Factoring is the mathematics of decomposition. It is the process of taking a mathematical expression and rewriting it as a product of simpler expressions, reversing the expansion that multiplication produces, looking beneath the surface of a combined form to find the components whose multiplication built it. Where multiplication assembles factors into a product, factoring disassembles a product back into its factors. It is the inverse operation of expansion, the algebraic equivalent of asking not what a construction produces, but what it was built from, finding the hidden architecture within an expression that its combined form conceals. The simplest form of factoring identifies a common factor shared by every term in an expression and draws it out in front. The expression 6x squared plus 9x contains 3x as a factor of both terms because 6x squared is 3x multiplied by 2x, and 9x is 3x multiplied by 3. Drawing 3x out as a common factor rewrites the expression as 3x multiplied by the quantity 2x plus 3. This single step simplifies the expression, reduces its apparent complexity, and often reveals structural features that were invisible before. Finding the greatest common factor, the largest expression that divides every term, is always the first technique applied when factoring, the step that clears away the most accessible layer of shared structure before deeper methods are needed. Factoring trinomials, expressions of degree 2 with 3 terms, requires identifying two expressions whose product reconstructs the original. The process searches for two numbers or expressions whose product equals the constant term and whose sum equals the coefficient of the middle term. Guided by the relationship between the expanded and factored forms of a quadratic expression. This search is both algorithmic and intuitive, and its fluency develops with practice until the factored form of common trinomials becomes recognizable almost immediately. Special cases simplify the process further. The difference of two squares factors into the product of their sum and difference, a compact and elegant identity that appears throughout algebra. Perfect square trinomials factor into the square of a binomial, collapsing three terms into a single squared expression. Factoring is not merely a technique for simplifying expressions. It is a tool for solving equations. When a polynomial is expressed as a product of factors set equal to 0, the zero product property applies, asserting that if a product of quantities is 0, at least one of those quantities must itself be 0. This reduces the problem of solving a polynomial equation to the simpler problem of solving several linear or lower degree equations, each obtained by setting one factor equal to 0. The solutions appear naturally and directly from the factored form, without any additional algebraic manipulation. In number theory, factoring integers into primes reveals their fundamental structure. In calculus, factoring simplifies expressions before differentiation and integration. In abstract algebra, the concept generalizes to polynomials over arbitrary fields and to elements of rings. Quadratic equations are the mathematics of curved relationships. They are the equations in which the variable appears raised to the second power, producing not the straight uniform behavior of linear equation, but a graceful arc, a curve that rises and falls, reaches a peak or a trough, and crosses the horizontal axis at points that carry deep mathematical meaning. The word quadratic derives from the Latin for square, reflecting the squared variable that defines the family and the shapes these equations describe. The parabolas traced by their graphs appear throughout the natural world with a frequency that makes them among the most encountered curves in all of mathematics. The standard form of a quadratic equation places all terms on one side with 0 on the other, organizing the expression as the sum of a squared term, a linear term, and a constant, each multiplied by its own coefficient. This organization makes the degree of the equation immediately visible and provides the structure needed for the various methods of solution. The graph of the corresponding quadratic function is always a parabola, a symmetric curve opening upward when the coefficient of the squared term is positive, and downward when it is negative. The vertex, the point where the parabola reaches its highest or lowest value, sits at the axis of symmetry, the vertical line that divides the curve into two perfectly mirrored halves. The solutions to a quadratic equation are the values of the variable that make the equation true, the points where the parabola crosses the horizontal axis. These are the roots of the equation, and their number and nature depend on a single expression calculated from the equation's coefficients. When two distinct real roots exist, the parabola crosses the axis at two separate points. When exactly one root exists, the parabola touches the axis at precisely one point, its vertex resting exactly on the boundary. When no real roots exist, the parabola misses the axis entirely, arching above or below it without intersection, and the solutions exist only within the extended number system that includes complex numbers. Several methods of solution are available, each suited to different circumstances. Factoring works swiftly when the equation factors cleanly into a product of simple expressions. Completing the square rewrites the quadratic in a form that makes the solution immediately visible, transforming the equation through a specific algebraic manipulation into a perfect square set equal to a constant. This method also reveals the vertex of the parabola directly, connecting the algebraic and geometric descriptions of the equation in a single procedure. The quadratic formula, derived by applying completing the square to the general form of the equation, provides a universal method that works for any quadratic equation regardless of whether it factors conveniently. It expresses both solutions in terms of the equation's coefficients, reducing them in a single calculation. In physics, quadratic equations describe the trajectories of projectiles. the behavior of accelerating objects, and the shapes of reflective surfaces. In engineering and design, parabolas appear in bridges, satellite dishes, and optical instruments. The quadratic formula is the universal solution to every quadratic equation ever written. It is a single algebraic expression that takes the coefficients of any quadratic equation and returns its solutions directly, without factoring, without guessing, without any trial and error. It is one of the most memorized formulas in all of mathematics, recognized across centuries and cultures, taught in classrooms on every continent, and relied upon wherever quadratic equations arise. Its derivation is an exercise in algebraic elegance. Its application is an exercise in reliable, systematic power. The formula emerges from the method of completing the square applied to the most general possible quadratic equation. Rather than solving a specific equation with specific coefficients, completing the square is applied to an equation where the coefficients are left as letters, each one representing any possible value. The algebraic manipulation proceeds exactly as it would for specific numbers, isolating the squared variable, adjusting the expression to form a perfect square, and taking the square root of both sides. What emerges at the end of this general derivation is the formula expressed in terms of the original coefficient letters, valid for every quadratic equation simultaneously. The derivation is not merely a proof that the formula works. It is an explanation of why it must work, a revelation of the structure that all quadratic equations share beneath their individual variation. The formula itself contains within it a smaller expression of particular significance, the part beneath the square root sign, formed from the coefficients through a specific combination of squaring, multiplying, and subtracting. This expression is called the discriminant, and it carries alone the information that determines the nature of the solutions before the full formula is even evaluated. When the discriminant is positive, the square root produces a real number, and the formula yields two distinct real solutions corresponding to 2 points where the parabola crosses the horizontal axis. When the discriminant is exactly 0, the square root vanishes and the formula yields one repeated solution corresponding to the parabola touching the axis at exactly 1 point. When the discriminant is negative, the square root reaches into the imaginary numbers and the formula yields two complex solutions corresponding to a parabola that never crosses the real axis at all. This classification by discriminant is one of the earliest and most natural encounters with the idea that solutions to equations need not always be real numbers, that the number system must sometimes be extended to accommodate every possible answer. The quadratic formula is the doorway through which the complex numbers first appear as necessary rather than merely curious. The formula also demonstrates something deeper about mathematics as a discipline. The act of solving a general case rather than a specific one, of deriving a result that works for every member of a family of problems simultaneously, is characteristic of how mathematical thinking advances. Rather than solving each quadratic equation individually, the formula solves all of them at once. Logarithms. Logarithms are the mathematics of inverse exponentiation. They are the operation that answers the question exponentiation leaves open, not what power does a base produce when raised, but to what power must a base be raised to produce a given result. Where an exponent asks a base to grow by repeated multiplication and returns the result, a logarithm is handed the result and asked to recover the exponent. The two operations are perfect inverses of one another, mirror images in the same sense that addition and subtraction, multiplication and division are mirror images. Logarithms complete the family of inverse relationships that runs through arithmetic, extending it into the domain of exponential growth. The notation carries the essential information compactly. The logarithm base 10 of 1000 is 3 because 10 raised to the power of 3 is 1000. The logarithm base 2 of 32 is 5 because 2 raised to the power of 5 is 32. The base of the logarithm is the same base that would appear in the corresponding exponential expression, and the logarithm returns the exponent that produces the given input. Every logarithmic statement has an equivalent exponential statement, and moving fluently between these two forms is the first and most important skill in working with logarithms. The historical motivation for logarithms was intensely practical. Before calculating machines existed, multiplying and dividing very large numbers was a laborious and error-prone process. Logarithms offered a remarkable shortcut rooted in one of their most fundamental properties. The logarithm of a product equals the sum of the logarithms of the factors. The logarithm of a quotient equals the difference of the logarithms. These properties transform multiplication into addition and division into subtraction, reducing the most demanding arithmetic operations to simpler ones. Tables of logarithms were compiled with enormous care and used by navigators, astronomers, engineers, and scientists for centuries, allowing calculations that would otherwise require hours to be completed in minutes. The most naturally occurring base for logarithms is not 10, but an irrational number called e, approximately equal to 2.718, whose special properties make it the base of choice in calculus and mathematical analysis. The natural logarithm, the logarithm to base e, appears wherever exponential growth and decay are described mathematically. In population models, in radioactive decay, in compound interest calculations, and in the fundamental equations of thermodynamics and information theory. Its intimate relationship with the exponential function whose base is e gives it a central role in calculus that no other logarithm shares. Logarithms also provide the mathematical foundation for scales that compress enormous ranges of values into manageable forms. The decibel scale of sound intensity, the Richter scale of earthquake magnitude, and the pH scale of acidity all employ logarithmic compression, representing quantities that span many orders of magnitude as modest numbers on a human-readable scale. Sequences are the mathematics of ordered progression. They are lists of numbers arranged in a definite order, each one occupying a specific position in the list, each one potentially related to those before and after it by some rule or pattern. A sequence is not merely a collection of numbers. The order matters. The position of each element is part of its identity, and changing the arrangement changes the sequence into something fundamentally different. Sequences are among the oldest objects of mathematical study, appearing wherever patterns unfold in time, wherever processes generate values step by step, wherever the relationship between one term and the next reveals something meaningful about the structure of the whole. The terms of a sequence are its individual elements, referred to by their position. The first term, the second term, the third term, each one located by its index, a counting number that identifies where in the sequence it sits. A sequence can be described by an explicit formula, one that gives the value of the term directly from its position without requiring knowledge of any previous terms. It can also be described by a recursive formula, one that defines each term in relation to one or more of the terms that came before it, building the sequence forward step by step from its starting values. Both descriptions are legitimate and complete, and each has contexts where it is more natural or more useful than the other. The variety of sequences that arise naturally in mathematics is vast. Some sequences grow steadily upward by a constant amount with each step. Some grow by a constant ratio, multiplying by the same factor at every stage. Some oscillate, alternating between positive and negative values. Some converge, their terms drawing ever closer to a fixed value without ever quite reaching it. Some diverge, their terms growing without bound or fluctuating without settling. The behavior of a sequence as its terms extend toward infinity is one of the central questions in mathematical analysis, and the distinction between convergence and divergence carries profound implications for everything built upon sequences. Sequences also arise naturally outside pure mathematics. The Fibonacci sequence, in which each term is the sum of the two preceding terms, appears in the spiral arrangements of seeds in sunflowers, the branching of trees, and the proportions of certain shells. Sequences of partial sums describe the accumulation of infinite processes. Sequences of approximation are the mechanism by which computers and calculators evaluate functions to any desired precision. Sequences of measurements over time are the raw data of scientific observation, the record from which patterns are extracted and models are built. The study of sequences connects naturally and deeply to the concept of functions. A sequence is, formally, a function whose domain is the natural numbers, a rule that assigns a value to each counting number in order. Every technique and every question developed in the study of functions applies to sequences translated from the continuous language of functions into the discrete language of ordered lists. Series. Series are the mathematics of accumulated sums. They are what emerges when the terms of a sequence are not merely listed and observed, but added together, one after another, building a cumulative total that grows with each new term included. A sequence asks what each term is. A series asks what all the terms amount to when combined. The shift from sequence to series is the shift from observation to accumulation, from listing to totaling, from the individual value at each position to the running sum of every value up to and including that position. It is a natural and profound step, and it opens one of the richest areas of mathematical analysis. The partial sums of a series are the totals obtained by stopping the addition at various points. The first partial sum is simply the first term. The second partial sum is the sum of the first two terms. The third is the sum of the first three, and so on. These partial sums are themselves a sequence, growing with each additional term, and their behavior, as more and more terms are included, is the central question that the study of series addresses. A series is finite when the number of terms is limited, and the total is simply the result of adding them all. A series is infinite when the terms continue without end, and the question of what the total becomes is no longer straightforward. The behavior of an infinite series hinges on whether its sequence of partial sums converges or diverges. If the partial sums approach a fixed value ever more closely as more terms are added, the series is said to converge, and that fixed value is the sum of the series, the total that the infinite accumulation approaches as its limit. If the partial sums grow without bound or fluctuate without settling, the series diverges and no finite sum can be assigned to it. The distinction between convergence and divergence is not always obvious from inspection, and mathematics has developed a rich collection of tests and techniques for determining which behavior an infinite series exhibits. The most immediately surprising result in the study of series is that an infinite collection of numbers can add to a finite total. The geometric series formed by adding 1/2 plus 1/4 plus 1/8, each term half the previous, adds to exactly 1, a finite result despite involving infinitely many terms. This convergence is not a paradox, but a precise mathematical fact, provable by examining the partial sums and observing that they approach 1 ever more closely without ever exceeding it. Series appear throughout mathematics with extraordinary frequency. Power series represent functions as infinite sums of polynomial terms, allowing functions of every kind to be analyzed through the tools of polynomial arithmetic. Fourier series decompose periodic functions into infinite sums of trigonometric terms, providing the mathematical foundation for signal processing, acoustics, and wave analysis. Arithmetic progressions. Arithmetic progressions are the mathematics of steady accumulation. They are sequences in which each term is obtained from the previous one by adding the same fixed amount, advancing by constant steps from beginning to end, producing a pattern of perfect regularity that extends as far as the sequence continues. The fixed amount added at each step is called the common difference, and it is the defining characteristic of the progression, the single number that determines the entire sequence once a starting value is established. Arithmetic progressions are among the most orderly structures in all of mathematics, their terms marching forward with the even, unhurried pace of a constant rhythm. The simplest arithmetic progressions are already familiar from early encounters with numbers. The sequence of natural numbers 1, 2, 3, 4, 5 is an arithmetic progression with a common difference of 1, each term advancing by exactly 1 unit from the last. The sequence of even numbers 2, 4, 6, 8, 10 is an arithmetic progression with a common difference of 2. The sequence of odd numbers 1, 3, 5, 7, 9 is another, also advancing by 2 but beginning from 1. These foundational sequences of arithmetic are all arithmetic progressions, their regularity a reflection of the constant step size that defines them. The formula for the term at any position in an arithmetic progression follows directly from the definition. To reach the term at position n, one begins at the first term and adds the common difference n minus 1 times, once for each step taken after the starting point. This formula is explicit and immediate, requiring no knowledge of any previous terms, no recursive calculation, no step-by-step construction. It locates any term in the sequence directly from its position, transforming a question about the 100th or the 1000th term into a straightforward arithmetic calculation. The sum of the terms of an arithmetic progression, when a finite number of them are considered together, has an elegant formula discovered and verified through a beautifully simple observation. The young mathematician Carl Friedrich Gauss is said to have recognized as a child that the sum of the integers from 1 to 100 could be found by pairing each number with its counterpart from the other end of the sequence. 1 and 100 sum to 101, 2 and 99 sum to 101. Every pair across the 50 pairs in the sequence sums to the same total, making the overall sum 50 multiplied by 101. The general formula for any arithmetic series extends this insight, expressing the sum as the number of terms multiplied by the average of the first and last terms. Arithmetic progressions appear wherever quantities accumulate at a fixed rate. Simple interest grows arithmetically, adding the same fixed amount to a balance each period. Uniform motion covers arithmetic progressions of distance in equal intervals of time. Musical scales in equal temperament advance by equal frequency ratios. Geometric progressions Geometric progressions. Geometric progressions are the mathematics of proportional growth. They are sequences in which each term is obtained from the previous one, not by adding a fixed amount, but by multiplying by a fixed factor, scaling up or scaling down by the same ratio at every step. This common ratio, the single number by which each term is multiplied to produce the next, is the defining characteristic of a geometric progression, the engine of its behavior, the source of the dramatic and often surprising patterns it generates. Where arithmetic progressions advance by steady addition, geometric progressions advance by repeated scaling. And the difference between these two modes of growth is one of the most consequential distinctions in all of mathematics. The behavior of a geometric progression depends entirely on the value of the common ratio. When the ratio is greater than 1, the terms grow, each one larger than the last by the same multiplicative factor, the sequence accelerating outward without bound. When the ratio is exactly 1, every term equals the first, and the progression is the least interesting of all sequences, a constant repetition of the same value. When the ratio is between 0 and 1, the terms shrink with each step, each one a fixed fraction of the previous, approaching 0 without ever reaching it, the sequence decaying gradually toward nothing. When the ratio is negative, the terms alternate in sign, positive and negative in strict alternation, growing or shrinking depending on whether the magnitude of the ratio exceeds 1 or falls below it. The formula for any individual term in a geometric progression follows from the repeated multiplication that defines the sequence. The first term is the starting value. The second term is the first multiplied by the ratio. The third term is the first multiplied by the ratio twice. The term at any position is the first term multiplied by the ratio raised to a power 1 less than the position number. This formula reaches directly to any term in the progression without constructing every term before it, expressing the entire growth pattern in a single compact expression whose exponent carries all the positional information. The sum of a finite geometric progression has an elegant closed form that condenses what would otherwise be a long chain of additions into a single fraction. The derivation involves a beautiful algebraic trick of multiplying the sum by the ratio, observing that most terms then cancel between the original and the shifted sum, and solving for the remaining expression. This technique reveals not just the formula, but the elegant structure underlying it. Infinite geometric progressions whose common ratio falls strictly between -1 and 1 converge to a finite sum, their terms diminishing rapidly enough that the accumulation settles to a fixed limit. Compound interest, population growth, radioactive decay, the bouncing of a ball losing a fixed fraction of its height with each bounce, all of these processes are geometric progressions in disguise. Limits are the mathematics of approach. They are the formal description of what a quantity gets closer and closer to as something else changes, the value that a function or sequence inches toward without necessarily ever reaching, the destination that a mathematical process aims at as it runs forward without end. A limit does not ask where something is. It asks where something is going, what value it is approaching, what it would reach if the process it describes could be carried to its ultimate conclusion. This shift in perspective, from the value at a point to the value approached near a point, is one of the deepest conceptual moves in all of mathematics. The intuition behind a limit is more natural than the formal definition might suggest. Imagine walking toward a wall, covering half the remaining distance with each step. After one step, half the distance remains. After 2 steps, 1/4 remains. After 3, 1/8. The steps grow shorter and shorter, each one bringing the walker closer to the wall. The total distance covered approaching the full gap without any single step completing the journey. The limit of the total distance covered is the full distance to the wall, even though no individual step reaches it. The limit is the destination of the process, the value the accumulated steps converge toward. The formal definition of a limit captures this intuition with precision that leaves no room for ambiguity. A function approaches a limit as the input approaches a particular value if, for any desired degree of closeness to the limit, a corresponding degree of closeness of the input to the target value can be found that guarantees the output is within the desired range. This epsilon-delta definition, developed rigorously in the 19th century, replaced the intuitive but imprecise language of infinitely small quantities with a rigorous standard that mathematics could build upon without contradiction. Limits behave predictably under the standard arithmetic operations. The limit of a sum is the sum of the limits. The limit of a product is the product of the limits. The limit of a quotient is the quotient of the limits, provided the denominator does not approach 0. These properties allow limits of complex expressions to be evaluated by decomposing them into simpler parts, each handled separately. Special forms where both numerator and denominator approach zero simultaneously, called indeterminate forms, require more careful treatment, and the techniques developed to resolve them are among the most elegant and frequently used in calculus. Limits are also the foundation upon which every other concept of calculus is built. The derivative is defined as the limit of a ratio of changes as the change in input shrinks towards zero. The integral is defined as the limit of a sum of products as the number of terms grows without bound. Continuity is defined in terms of limits. Convergence of series is defined in terms of limits. The entire apparatus of calculus, and much of mathematical analysis beyond it, rests on this single, carefully defined concept. Continuity. Continuity is the mathematics of unbroken flow. It is the property that describes functions whose graphs can be traced without lifting the pen from the page, whose values change without sudden jumps or gaps, whose behavior at every point connects smoothly and seamlessly to the behavior at every neighboring point. A continuous function is one that has no interruptions, no teleportations, no moments where the output leaps abruptly from one value to a distant other without passing through everything in between. Continuity is not merely a visual impression of smoothness. It is a precise mathematical property defined in terms of limits that captures the idea of unbroken connection with exact and testable conditions. The formal definition of continuity at a point requires three conditions to hold simultaneously. The function must be defined at the point, producing some output value when the input is applied. The limit of the function as the input approaches that point must exist. The function's values must converge toward a single number as the input closes in from either side, and the limit and the actual value must agree. The number the function approaches must equal the number the function produces at the point itself. When all three conditions hold, the function is continuous at that point, and the graph passes through smoothly without interruption. When any one of the three fails, a discontinuity occurs, and the unbroken flow is broken. Discontinuities take several distinct forms, each with its own character and cause. A removable discontinuity occurs where the function's limit exists, but the function value at the point is either absent or different from the limit, a single isolated break that could be repaired by redefining the function at that one point. A jump discontinuity occurs where the function approaches different values from the left and the right, the two sides of the input approaching the point from opposite directions, arriving at different destinations, the graph leaping from one level to another. An infinite discontinuity occurs where the function grows without bound as the input approaches the point, the graph shooting toward infinity rather than settling at any finite value. A function that is continuous at every point in its domain is called a continuous function, and such functions possess properties of remarkable power and elegance. The intermediate value theorem states that a continuous function on a closed interval takes every value between its values at the endpoints, passing through every intermediate level at least once. If a continuous function is positive at one endpoint and negative at another, it must be zero somewhere in between. This result, intuitive in its geometric reading, has profound consequences for proving the existence of solutions to equations and fixed points of mappings. Continuity also interacts deeply with the other concepts of calculus. Differentiability implies continuity. A function that has a well-defined rate of change at every point must be continuous. Integrability of continuous functions on closed intervals is guaranteed. The derivative is the mathematics of instantaneous change. It is the measure of how rapidly a function's output is changing at a single precise moment, the rate at which one quantity is responding to infinitesimally small changes in another, the slope of a curve not across a broad interval but at a single point, where slope measures the steepness of a straight line uniformly along its entire length. The derivative measures the steepness of a curve at each individual point, recognizing that curves bend and that their rate of change is itself a changing quantity. The derivative captures that local momentary point-by-point rate of change with a precision that transforms the intuitive idea of speed into a rigorous mathematical object. The conceptual foundation of the derivative begins with the slope of a straight line connecting 2 points on a curve. This line, called a secant, cuts across the curve and measures the average rate of change between the 2 points it connects. As the 2 points are moved closer together, the secant line rotates, its slope adjusting to reflect the average rate of change over a shrinking interval. As the distance between the points approaches zero, the secant line approaches a limiting position, a line that touches the curve at exactly 1 point, and whose slope matches the curve's direction at that precise location. This limiting line is the tangent line, and its slope is the derivative. The formal definition translates this geometric picture into algebraic language through the machinery of limits. The derivative of a function at a point is the limit of the ratio of the change in the function's output to the change in its input as that change in input approaches zero. This ratio for any positive change in input measures the average rate of change over the corresponding interval. Taking the limit as the interval shrinks to nothing extracts the instantaneous rate from the average, producing the derivative as a precise numerical value at each point where the limit exists. A function whose derivative exists at a point is said to be differentiable there, and differentiability is a stronger condition than continuity. Every differentiable function is continuous, but not every continuous function is differentiable. Functions with sharp corners or cusps are continuous, but lack a well-defined tangent direction at the corner, and therefore have no derivative at that point. The derivative requires not just that the function be defined and unbroken, but that its direction be well-defined and stable as the point is approached. The derivative function, obtained by finding the derivative at every point where it exists, is itself a function, and it can be differentiated again to produce a second derivative, measuring the rate of change of the rate of change. In physics, if position is a function of time, the derivative of position is velocity, the instantaneous rate of change of position, and the derivative of velocity is acceleration, the instantaneous rate of change of velocity. Differentiation rules. Differentiation rules are the grammar of calculus. They are the systematic collection of techniques that allow derivatives to be computed efficiently and reliably, without returning to the limit definition for every new function encountered. Just as arithmetic has rules that allow calculations to proceed without reconstructing the foundations of number theory at each step, differentiation rules allow the machinery of calculus to operate smoothly and swiftly across the enormous variety of functions that mathematics and its applications produce. They transform differentiation from a laborious limit calculation into a fluent and practiced skill, a set of patterns learned deeply enough to become almost automatic. The most fundamental rule addresses the simplest functions. The derivative of any constant is zero, because a constant function never changes, its output remaining fixed regardless of the input, its rate of change at every point identically nothing. The derivative of a variable raised to a whole number power follows a pattern of remarkable simplicity and elegance, bringing the exponent down as a coefficient and reducing the power by 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. The derivative of x to the fourth is 4x cubed. This power rule extends beyond whole number exponents to fractional and negative powers, with the same formula unchanged, unifying an enormous class of functions under a single differentiation procedure. The rules for combining functions through addition and scalar multiplication follow naturally from the properties of limits. The derivative of a sum of functions is the sum of their derivatives, each term differentiated independently. The derivative of a constant multiple of a function is that constant multiplied by the derivative of the function. These two rules together mean that polynomials can be differentiated term by term, each power handled separately by the power rule, making the differentiation of polynomial functions an immediate and mechanical process. The product rule addresses the derivative of two functions multiplied together, and its form is slightly less intuitive than the additive rules. Differentiating a product requires combining the derivative of the first function multiplied by the second with the first function multiplied by the derivative of the second. The chain rule addresses the derivative of a function composed within another function, the case where one function's output serves as another function's input. The derivative of the outer function evaluated at the inner function, multiplied by the derivative of the inner function, gives the derivative of the composition. These two rules together reach almost every function encountered in mathematics, their combination generating derivatives of great complexity from a small number of basic patterns. Special rules for the trigonometric, exponential, and logarithmic functions complete the core collection. The exponential function, whose base is e, holds the remarkable property of being its own derivative, unchanged by differentiation, the only function that occupies this unique fixed point of the differentiation operation. The integral. The integral is the mathematics of accumulation. It is the operation that measures the total amount of something that builds up continuously over an interval, the sum of infinitely many infinitesimally small contributions, each one too small to measure individually, but together amounting to a precise and finite whole, where the derivative dissects a function at a single point. asking how rapidly it changes there. The integral takes the broad view, spanning an entire interval, gathering every contribution the function makes across its range and producing a single number that represents the total accumulation. The derivative and the integral are the two fundamental operations of calculus, and their relationship to one another is one of the most profound discoveries in the history of mathematics. The geometric interpretation of the integral is immediate and natural. For a function whose output is always positive, the integral over an interval is the area enclosed between the graph of the function and the horizontal axis, the region bounded above by the curve and below by the baseline. This area represents the total accumulation of the function's values across the interval, each vertical strip of infinitesimal width contributing its height multiplied by its width to the total. The integral is the limit of this summation process, as the strips are made infinitely thin and infinitely numerous, their total converging to the exact area with perfect precision. The formal definition captures this geometric picture through the concept of a Riemann sum. The interval is divided into subintervals, each one small enough that the function's value within it is approximately constant. The area of the rectangle built on each subinterval, with height equal to the subinterval's length, approximates the area under the curve over that small portion. Summing all these rectangles gives an approximation to the total area. Taking the limit as the number of subintervals grows without bound, and each subinterval's width shrinks towards zero extracts the exact value, the integral from the sequence of improving approximations, the integral is not limited to computing areas, it measures any quantity that accumulates continuously from contributions spread across an interval. Distance traveled by an object moving at varying speed, total mass of an object with varying density, work done by a force that changes along a path, electric charge accumulated over time. In each of these cases, the accumulation is exactly what the integral computes, its generality making it one of the most broadly applicable tools in all of applied mathematics. Two types of integrals carry distinct but related meanings. The indefinite integral of a function is the family of functions whose derivative equals the original function. The antiderivative, a function undoing what differentiation did. The definite integral over a specific interval is the numerical value of the total accumulation computed by evaluating the antiderivative at the interval's endpoints and taking their difference. The fundamental theorem of calculus. The fundamental theorem of calculus is the great unification of mathematics. It is the result that reveals differentiation and integration, the two central operations of calculus, to be not merely related, but inverse to one another in the deepest possible sense. Mirror operations that undo each other in the same way addition and subtraction, multiplication and division undo each other. Before this theorem was understood, differentiation and integration appeared as separate enterprises, each with its own motivation, its own geometric meaning, its own methods of calculation. The theorem revealed them as two faces of the same object, and in doing so transformed calculus from a collection of clever techniques into a unified and coherent theory of continuous change. The theorem comes in two parts, each illuminating a different facet of the relationship between the operations. The first part addresses the derivative of a function defined as an integral whose upper limit varies. If a function is constructed by integrating some continuous function from a fixed starting point up to a variable endpoint, then differentiating that constructed function recovers the original function being integrated. Accumulation and rate of change cancel one another perfectly. The integral builds up a quantity continuously, and the derivative measures exactly how fast it is building, returning the very function whose accumulated contributions produce the integral. This result, elegant in its statement, is remarkable in its implication. It means that integration and differentiation are inverse processes, that each one undoes what the second part translates this abstract relationship into a practical computational tool of extraordinary power. It establishes that the definite integral of a function over an interval, the total accumulation from one endpoint to the other, can be computed by finding an antiderivative of the function and evaluating it at the two endpoints. The integral, which by definition is the limit of infinitely many increasingly refined sums, collapses to a simple subtraction of two values. This transformation is the engine of integral calculus in practice, rather than computing limits of Riemann sums directly, which is laborious for all but the simplest functions. The second part of the fundamental theorem makes integration as accessible as differentiation. The historical significance of this theorem cannot be separated from the names of the two mathematicians who developed calculus. Independently and whose work together established the foundation of the subject. Isaac Newton approached the relationship from the perspective of motion and physical change, understanding differentiation and integration as operations on quantities that flowed and accumulated in time. Gottfried Wilhelm Leibniz approached the same relationship through the geometry of curves and areas, developing the notation that remains standard today. Both arrived at the fundamental theorem, and both recognized its central importance to the entire enterprise. Every application of integral calculus, every area computed, every volume found, every physical quantity accumulated from a continuous distribution, rests ultimately on this theorem. It is the bridge between the local and the global, between the instantaneous rate and the total accumulation. Probability. Probability is the mathematics of uncertainty. It is the formal framework for reasoning about outcomes that are not predetermined events whose occurrence cannot be known in advance, but whose likelihood can be measured, compared, and calculated with precision. Probability does not eliminate uncertainty. It does not transform the unknown into the known. It quantifies uncertainty, assigns it a number, places it on a scale from 0 to 1, and makes it tractable, allowing decisions to be made rationally and predictions to be formed carefully even when the future remains genuinely open. It is the branch of mathematics that learned to work with what is not yet determined, and in doing so became indispensable to science, philosophy, and everyday reasoning. The scale of probability is fixed and universal. An event with probability 0 is impossible, certain never to occur within the framework being considered. An event with probability 1 is certain, guaranteed to occur without exception. Every other event occupies some position between these extremes. Its probability a number between 0 and 1 that reflects how likely it is relative to the complete range of possible outcomes. The probability of an event and the probability of its complement, the event not occurring, always sum to exactly 1. Because in any given trial, either the event occurs or it does not, and together these two possibilities account for every possible outcome. The simplest setting for probability is one where all outcomes are equally likely, each one as probable as every other, the idealized symmetry of a fair coin or an unbiased die. In this setting, the probability of any event is simply the ratio of favorable outcomes to total outcomes, a fraction whose numerator counts the ways the event can occur and whose denominator counts the total number of equally likely possibilities. This classical formula, elegant in its simplicity, provides the foundation from which more general and more powerful theories of probability are built. As situations grow more complex, the rules governing probability combine and extend. The probability of two independent events both occurring is the product of their individual probabilities. The probability of at least one of two mutually exclusive events occurring is the sum of their individual probabilities. When events are neither independent nor mutually exclusive, the rules require adjustment, accounting for the ways events interact and influence one another. Conditional probability, the probability of one event given that another has already occurred, captures the way new information updates the likelihood of outcomes, and its precise formulation leads directly to Bayes' theorem, one of the most powerful and consequential results in all of probability theory. Probability theory also provides the mathematical foundation for statistics, the discipline of drawing conclusions from data. Random variables, expected values, distributions, and confidence intervals all rest on the framework of probability, each one an extension of the basic idea of assigning numerical likelihoods to uncertain outcomes. From quantum mechanics to insurance, from weather forecasting to machine learning, probability governs every domain where the future is not yet written.